We'll get started in 1 minute if you want to get seated. I'll give a few safety announcements now, though. Given that we're in earthquake territory, and let's hope there's no fire. There's an exit there, an exit there. If you get really excited about the talk and somebody needs the defibrillator, it's out the door just about 15 feet that direction, mounted on the wall. If anybody feels unsafe here or at the conference throughout the venue, there are signs with contact information to report your concerns with safety. There's one taped on the back door. Okay, it's our official start time. Welcome to the Cloud Native track at SCaLE. Our next talk featuring Josh Berkus is on what you see here, how to provision your hardware with a container. Now, Josh is one of my personal favorites at SCaLE, and I think I see many of you who are repeat visitors who probably know this, that he's been giving talks here for over a decade. But the nice thing is that it's not the same thing over and over, and I think he's particularly good at spotting new and useful technologies early. You know, the first talks I went to from Josh were on Postgres, but later moving to containers, Kubernetes, and Cloud Native track talks. And today's topic, I think, is pretty unique, that it isn't typically covered at tech conferences. If you don't mind, save any questions to the end, and I'll turn it over to Josh. Can we give him a round of applause? If you do want to ask questions, please raise your hand so I can give you the mic and your question gets recorded.
Yep. Thank you, Steve. Am I loud and clear in the back? Awesome. Thank you. So let's talk about a little use case here. So both my wife and I work from home. We have separate offices on different floors of the house. But one of the things that's come up recently is we don't want to listen to Spotify anymore because issues. And we actually have this huge CD collection, including a whole lot of folk music that's no longer available. And so we'd really honestly like to have some kind of a music server that we could both share in the house, right? Because, I don't know, something like, 60,000 tracks, we might as well listen to our own music. But that's actually going to require some kind of a music server device. And since I've been experimenting a little bit with Bootsy, which you're about to hear about, I decided to actually make this a test case for, building this. So, I bought myself a little B-Link, which you can see right here. You can come up and look at the hardware later if you're in the back. So just a little B-Link x86 machine. And then, I did what anybody would do, which is I wrote some code and config stuff, and I packaged it up as a container, and then I used that to produce an ISO, and I went ahead and installed it, imaged the system. And a lot of you who are sysadmins, how many people is a sysadmin? Yeah, are going to be like, hey, wait a minute. What was this part? What are you doing there? Why? How is a container involved? Let me explain. Except to explain, I'm going to have to do a little bit of a tangent. So I hope you're ready for this tangent, where I'm going to talk about the history of Linux deployment technology, all of which I was personally present for. So this is my memory lane here. So how many people here have been doing Linux since the 90s? Do you remember having to regularly compile your own kernel in order to install it on the hardware you actually had? Yeah, in the mid-90s, that was how I started with Linux. You literally had to compile everything. So installing a new system was like a 3-day weekend, right? Because the compile often didn't work the first time you did it, right? And then you had to start over again. It was going to be another 13 hours, right? So that wasn't a lot of fun. And so what happened was in the mid-late 90s, Red Hat introduced packages, followed closely by Debian and SUSE and that sort of thing. So the idea of having actual binary packages for a lot of components of the system. That was a huge improvement, right? Installing a new Linux system went from a 13, 14-hour affair to being a 3 to 4 hour affair with a lot more reliability. However, going through those interactive menus and selecting every single package that you needed was really, really tedious, right? So a bunch of folks, including some folks I know, came up with this thing called configuration management, right? We're like, hey, we're going to have some code, and the code is going to select all of the packages that we're going to install, right? And that way, it's 3 to 4 hours, but it's not like 4 hours of interactive work, right? It's 4 hours where the computer is running, and we're just paying attention to it to see if it crashes, right? So again, another big improvement. However, still some problems, right, with the configuration management package thing, right? Number one is, it's fine if you're installing 1 machine or 2 machines or 4 machines, but what if I have to install 1,000 machines, right? You have a certain limited amount of parallelism and it's just too slow. And the other problem is you think of packages as binary things that are just being copied out of the file system, but unfortunately that's not real OS packages, right? In the RPMs, for example, they have this thing called the post-install script, which often does a lot of interactive stuff, the output of which is not determinative, which means you can get unique failures on each system, which it is not able, the individual system is not able to recover from, right? Again, one system, not terrible, but if you're doing 1,000 systems and 105 of them each have their own individual unique failures, you're in for a bad couple of weeks. Parallelization is challenging, in terms of imaging a whole bunch of systems, and we'll get into this there. There's no concept of rollbacks, right? If you start imaging, installing a system, and something goes wrong, you can't just snap back to the system's previous good state. So then we got the cloud, right? And with the cloud brought with it some actual improvements in installing, which is that you could actually use whatever your cloud provider was, you could use their native configuration system in order to define a VM image that had all of the software that you wanted, build that VM image, and then just deploy that to virtual cloud instances, right? This was a huge improvement in reliability and scalability. However, it still had some problems. Number one, each cloud provider has their own set of proprietary tools for building this, right? Later on, we got Terraform and stuff to actually make it less proprietary. Those images are really slow to build, relatively speaking. These large images are hard to distribute. They only work on that particular cloud. They don't work on other clouds, let alone on bare metal. And we still get no rollbacks. If we want to re-image an existing system, right? Because they're assuming you're going to deploy a new virtual machine, right? Which is fine if that's what you're doing. But if you're going to mix bare metal with cloud, bare metal, you want to think about rollbacks. So, in the meantime, in the area I was more working on, because I wasn't a sysadmin anymore, I was a database engineer, et cetera, we got this thing called application containers, right? Docker. Right, so we've now got these binary images, these tarballs, to distribute an installed and configured application. And this had a lot of advantages, right? We had very simple, easy to learn build tools based roughly on Bash. The images build a heck of a lot faster, right? Easily 2 orders of magnitude faster. The smaller images make it easier to distribute. You could use this thing called the container registry that was just like, a package mirror or whatever, but it's for a whole, system. And containers were useful both in the cloud and on bare metal, right? You could move them anywhere around. Bare metal, cloud, edge device, whatever, cross-compile them to different architecture, that sort of thing. And importantly, because it was a binary image being installed sort of bitwise, you could actually roll it back, right? You distribute version 7 of your application image. It turns out to be broken. You can roll back to version 6 pretty quickly. So this is terrific. So wouldn't it be nice if not just for an application, but if we could do that for the whole system, whether it's a cloud system or a bare metal system? And that is where bootc comes in. So bootc is the concept of bootable containers, right? The idea is that you can build a container image and then you can boot it on a virtual system or a real system as an OS. It deploys the containers as system images. It manages system status, updates, rollbacks, everything else. And importantly, it supports rollback. So that I can image even a bare metal system and then roll back to the last good state if it turns out that I made a mistake. The way that it does this is, so your standard Docker application container, right, has a base image which consists of basically Linux user space. And then all of your app code on top of that base image, right? A bootable container contains those things, but we are also copying kernel space into it because we have to be able to boot it, right? So you have the bootloader and basically the whole Linux kernel. So this image is going to be significantly larger than you used to with application containers in order to make it bootable. But from the outside, aside from the larger size, as far as container registries are concerned, as far as container tools are concerned, it looks just like an application container. So, now that we have bootc, let's talk about actually building that system, right? So, this is again our initial provisioning, right? So I have some code. I use the code to build a container. I used the container to create an ISO because I'm deploying it to an unprovisioned system on my desk, and then provision that to my system. Now, I need to talk about this step, container to ISO, right? Because it's not actually that simple, unfortunately. We have this thing in the middle called bootc image builder. Because we're taking a container, right, and from that container we can actually produce, I don't know, like 11 or 12 different kinds of system images. If we actually look here, let me show you a fun little tool called Podman Desktop, which has plugins for a lot of these things. And if I take, these are my bootable container images that I have in my system right here. So like I'm going to take CentOS here, and if I want to actually build a new bootable OS image, right, I can do all of the common system image formats, including QCOW for, basic VM, VDMK for VirtualBox, or, Anaconda ISO installer for installing to hard drive, plus some other formats for doing more sophisticated installs. So, the problem we discovered with that for a command line tool is that being able to build all of these different formats requires a lot of different build tools, some of which are actually really annoying to configure correctly. And so what the bootc team did was they created a container image called bootc image builder that contains all of those VM and ISO building tools. So I'm actually taking a container image, feeding that container image into another container, having it process that and output an ISO, which is a fun little bit of bootstrap levitation. However, I'm not actually going to demo that because those two steps are pretty slow. I clocked it to see if I actually could demo building the ISO in here. It's like 15 minutes, that sort of thing, which is not terrible if you're doing it like yourself in the office, but for the middle of a conference presentation is not great. So you're not actually going to see that part live. And also the other reason you're not going to see that part live is in the future that's not what you're going to be doing. What I wanted to do, the original path was, oh, by the way, here's a little shot from the middle of me installing everything. So this is it launching the Anaconda installer. I have this little micro Raspberry Pi screen, which works well for this. What you should do in the future, and I ran into a couple of blockers on this, and Colin, who's one of the maintainers of bootc, is like working on stuff, which is what you really want to have happen is you build your container and then you push it to a container registry. And then what happens is you PXE boot the individual device, and it PXE boots into a very minimal bootstrap operating system that knows how to talk to the container registry. And so that communicates with the container registry, and all the bootstrap operating system has is what bootable container it's supposed to be running. It pulls down the bootable container, uses that to overwrite the file system, and then we are booted into the application server for the device. So expect that to be working in a couple of weeks. I'll update my repo with instructions for that once I've actually got that working. And that is the path for the future. Because while this looks more complicated as a path, the important thing is all of the slow steps happen without human oversight, right? The human just initiates, hey, we're booting a new system on this image, and then they don't pay any attention to it until it says it's up and ready, or that it's failed, right? And one of the other reasons why you want to do this is what you already do when you want to update the system, right? Because once you've got your bootc system up and running, anytime you want to push an update to what your device is running, right, you update your code and config, you build a new container, you push that to a container registry, the device communicates with a container registry. I think default is once a day. I don't remember how often it checks by default, but you can configure it twice a day, okay. But you can configure the interval at which it checks with the container registry, right? That's completely configurable. And then it updates its code and runs the new version of the application. I'm going to show you this interactively because obviously you don't want to wait hours for the update. This is the demo code. I'll go back to this in a minute, but in the meantime, let me show you the demo. So, first of all, like I said, I'm not going to actually interactively go through the setup because it takes too long, but I will show you all the code for this. So this is pushed to that repository. I have an explanation of what everything is. So one of the ways, if you're building an Anaconda ISO as your installation option, and the simpler way to handle it is this thing called the config toml file, and that contains the configuration for what your ISO image is going to look like aside from what's in the container, right? And so I've got in here of what kind of keyboard am I using, what time zone is it, what's the initial network setup, because you obviously need that or it can't communicate with anything else. Partitioning and and the modules for Anaconda. Most of this you'll recognize is I've embedded the kickstart file in the config toml, right? Because it's just easier to have everything in one file. And so for this demo, what this is building is not my music server, but a very simple web server thing. So here is our base bootable image. So the easiest way to get a bootable image is that you start from copying somebody else's bootable image, right? So this is Fedora version 43 bootc image, which is available from the Fedora project. You can get CentOS, you can get a bunch of other flavors, which I'll go over a little bit later in the presentation. And all we're doing here is we're installing Apache and auto-starting it. We're installing Apache, auto-starting it with an index.html that we've actually copied in. So here's that initial index.html, just a very basic web page. So copy in, push it over, boot up, and I've got a couple of things going on here you'll see in here. Because I wanted to do this without relying on the internet, I have a container registry running on my laptop. And you can see actually here, I have a lot of the commands I used to build it. Yeah, this is the next generation. The question was, is it similar to how you provision things with CoreOS? This is effectively the next generation from that. Yeah. This is actually the command that I used with bootc image builder in order to build the Anaconda image. Where it pulls it out and you have to give it a lot of configuration. This is for running the registration. Let's go ahead and, so I've got this on a cute little local network. And as you can see, my little web server is up and running, right? So here we go. That's all it does. But we could change it. So let's go ahead and update it. So I'm going to call this version 2. And somebody want to volunteer? How should we change the text here? What should we put in here? Yeah, okay. And I'm not going to go find the upside down exclamation point, sorry. Yep. Okay. So go ahead and save that. And then, let's see, is this still in my history? Yes. So let's build the new container file, which just has one new layer. Push it to my local registry. Now, let's go ahead and look at this. We're going to go ahead and, so I can actually show this to you rather than using the console on the device. Very insecure login, but it makes it easier for demos. So, as I mentioned, bootc is not just a way of building bootable containers, it is also a management utility on the booted system. So I can look at what the current bootc status is here, right? And it tells me which container image I'm running. That version number there is pulled from the Fedora base image because I haven't overridden it in my own image. So it's just going to inherit that version number from Fedora, although you also check the SHAs because, of course, I'm changing one layer on top, and so it's going to change over time. And you can actually see, how there is. So then we can go ahead and we can update this. And when I put in bootc update, what it's going to do is it's going to go to its original container registry, which is information it has saved. You can change that later on if you need to move where the container is kept. You can go ahead and update it, and it is going to fetch the new layer. And then it is going to apply that new layer virtually so that it is ready on reboot. So we've added this, and if you look at bootc status again, right, you can see, hey, this is the image we're currently running, but that's the image that's going to start up when we restart. And so yes, you do have to restart. So that'll take just a second. You can actually look at rebooting here. Okay, we're not ready yet. Are we up yet? Yeah?
What hardware are you running on? That's an AMD64, so it's not a Raspberry Pi.
Right, yeah, no, it's not. No, this is just a little B-Link x86 running, I don't know what it is, lightweight AMD server, that sort of thing. Yeah, no, but I mean, the thing is you can cross-compile, right? But cross-compiling involves its own troubleshooting. But you could run it on an ARM system if you're just ready to deal with the cross-compiling. Or if your development machine is also an ARM system, then you don't have to deal with cross-compiling, right? Yep. Yeah. Yeah. Yeah, the question was about doing rolling updates over a whole fleet of devices. And the answer is yes, and there are a couple of different projects to handle that. One of them is Kubestellar, and also another one called Fleet Manager, that are specifically to handle that situation, right? Because you're going to want a control plane that actually has an idea of managing your whole fleet. Yes, exactly. But it's an orchestrator for edge devices instead of an orchestrator for just containers, right? So if we look at bootc status in the rebooted system, we've got the new image booted into and the rollback image. And if we go ahead and reload, we now have version 2. Yep. Now, those of you who know your system control, know that there was a slightly faster way to do what I just did. So let's go ahead, we're going to do version 3, we're going to go ahead and push it. Which is that bootc now supports something called soft boot, which will do a lighter weight restart that does not involve a full power cycle if the changes that you've made don't require it, right? If you're making changes to the kernel and stuff, it still has to power cycle. But if all you're doing is changing application code, which is what you're doing most of the time, it doesn't have to. Oh, whoops. Yeah. And so that'll happen in one command, and it'll be significantly faster. Ta-da. Oh, give it just a second. Yep. So that boots up a lot faster. And we got version 3 here, right? So, one more thing. I mentioned rollback because that was part of the whole point of doing this, right, is to have rollback. So, how should we break this? How should we break this simple HTML file? Suggestions? Like what? I want to mess it up. Yeah? Yeah, okay. So, you know, say I screwed it up. And then we're going to go ahead and apply that. Okay, and give it just a second. There we go. Let's see how much that messed things up. Not a lot. The problem is that the Apache web server is really good at handling bad HTML. So here, let me do something I actually saved, which really does mess things up. Is it? No, it's 6. Ta-da. Okay, and there we go. And now let's check that out. Ta-da. Now, I could have avoided that. First of all, I could have avoided breaking into the first place, because one of the things I mentioned is testing, right? So we've been showing all this booting of the system, but one of the things I actually want to remind people of is, well, this is a bootable container that is booting to the system. It is also a container. So I could have tested that and avoided breaking the running system, right? Because oh wait, I need some ports here, don't I? Yeah. Oh, whoops. What happened there? So if I actually do that, I could have checked it in advance, and you can see I could have actually checked that and caught the problem before it deployed to the running system, because even though this is a bootable container, I can also run it as a regular container. And so run it through all of my CI stuff as a regular container on Argo or Tecton or whatever, in order to do testing before it gets deployed to a system. Or if I have to do special hardware things, then I can create a different kind of VM image out of it and do my testing on VM. Yeah, the question is, does it require Podman to understand that? I haven't tried to run one of these on Docker, but I don't know why it wouldn't work. You know, it just ignores the kernel stuff, basically. So if the system you're testing on is a radically different kernel version than the system you're deploying to, then that could be a problem in your test validity. So you want them to be at least fairly similar, right? But other than that. But I didn't test it. So that means I need to use, there we go, a very important feature here, which is rollback. And now you can see with the rollback, well, it actually doesn't tell me that it's going to boot into the rollback image. But we've got this rollback image, and we're going to go ahead and reboot. And that'll take just a minute. Yes? Yeah. Yeah, I'm not versioning the tags. The important thing to keep in mind is, by default, bootc is looking for latest. So if you're going to use actual version tags, which is an excellent practice, you need to also remember to update your latest version as latest, because it's looking for that latest tag. Yes? Yeah. Yes. Yeah. Yes. Yeah. Yes, the question was, can you label your images so that you actually know what the changes were in each version? And the answer again is yes. This is very similar to his question, right? Which is using more informative tags. But like I said, you have to keep in mind that bootc is also looking for that latest tag. So you want to make sure to apply the latest tag to the latest version as well. And the other thing is, by default, for space reasons, the default for bootc is it only holds on to 1 to 2 old versions. But that is a thing you can configure on the system. You can tell it to hold on to more versions, which would allow you to actually roll back further. And then what you would add to that rollback command is an SHA to tell it to which version to roll back to. So that should be rebooted and fixed. Oh, it is not rebooted and fixed. Oh, I'm in the wrong one. You're right. Thank you. There we go. And that is rolled back and fixed. So with that, let's go ahead and finish up our slides, and then I'll take the rest of the questions. So again, let me hold this up for a minute. So the code that I just used is on this repo. As I get my little music server up and running, I will add extra stuff to that for the further things for doing that. And so the update advantages are you're not going through choosing which things are getting updated and which things are not getting updated. One of the other things that I can't really demo in a simple example like this, but Fedora got an intern who worked on actually doing intelligent algorithmic image layering so that, at least for Fedora and CentOS systems, it actually arranges the layers in a way that for most users will result in doing updates that are the smallest that they can reasonably be, considering that a lot of underlying libraries and stuff are probably getting updated, et cetera. There's no possibility of a partial update, right? There's no possibility that like half my libraries are going to get updated and the other half are not, right? Either the whole thing gets updated or it doesn't get updated. One of the things is if the update actually fails, bootc will automatically roll back to the last good version. So if it refuses to boot, it'll automatically roll back. One of the other great features here that I'm not prepared to demo, but I'll talk about, is bootc switch. See, the idea of bootc switch is, I told you, I can configure where that container image is. Now, the idea, I can configure where that container image is. Now, obviously, one of the things I might be doing is just moving around where my image server is, right? But I'm not limited to that. I can tell it to use a different image, like a completely different image. Like say, I've got the operating system image 1 here. Like say, right now I've got the simple web server, right? But when I want to put the music server on there, I'm going to have a completely different application, and I'm not going to be running Apache. So obviously I could reinstall the system, but I don't have to. I just tell it to use a different image, and it pulls down the new image, and it does a bitwise change from the old image, and I am now running a different service. I can even do a wholesale change, right? Because right now this is running Fedora 43, but what if I decided, hey, this is a headless box, maybe I want to run CentOS instead? I can literally do that. That's going to be a big change. It's going to change a lot of bits, and it's going to pull down a lot of layers to do that, but it works. As a matter of fact, for some of the other bootc systems that didn't have installers, what they would tell you is install Fedora Silverblue and then have it pull down a new image. Yeah? Well, no, you have to reboot after the new image is installed. The other thing is, obviously I've been showing you all this for basically an edge device. This is not just for edge devices. Here at the conference, you will see talks about doing it on desktop devices, including things like the Fedora Atomic desktops and Bluefin. Also, gaming consoles. The Bazite project uses gaming consoles, and this is all bootc based. So, and let me actually, whoops, what just happened? Okay. Let me actually show you that. So this is not in the device. This is my laptop. So my laptop, oh, right, hold on. This is my laptop, which is running Bluefin. And you can see right here that, oh, I've got a pending systemd update. Okay. Aside from the pending systemd update, actually, here's my example of automated rollback. Shortly before the conference, I'm running on basically a 2-week-old version of Bluefin's skin of Fedora. And shortly before that, we actually got an update that broke systemd. And so my laptop just automatically rolled back. And so you see we've got the staged one that with an error message, and it's running on the last good version. And so I didn't bork my laptop and be unable to use it right before the conference. get rid of that. So, what's next from here? Well, for me, I need to finish provisioning my music server, at which point you won't see me bringing this little box on the road. I'll have to get a new box for on-the-road demos because it'll be at home and my sweetie will not let me take the music server away. So I need to actually, fix the, there. I'm probably actually going to use Quadlet and run the jukebox program in containers because it actually has several different components, but I haven't decided on that. Part of what I got down here was I got bogged down into the different open source music players there are, and I wasn't sure which one to use and how they actually get configured. And I also need to figure out a way for the storage to be separate from the rest of everything because I don't want to include all 50 gigabytes of soundtracks in my image. But that's coming. What's next for you is go ahead and try and play around with bootc. For a simple point-and-click version of doing a lot of this, you can use Podman Desktop and then install the bootc module for it to play around with bootable images, etc. And that avoids you having to actually come up with a long command line for using bootc image builder, etc. bootc, open source project, CNCF project. So please, if you get into this, join in, ask questions, become part of the community. And with that, we have time for you to ask me questions.
So I think the description said this is also good for VMs and physical boxes. So I think a lot of people are kind of frustrated with the state of some of the auto deployment tools, especially in the Red Hat family. They're kind of not great. And junior admins are just completely unable, and AI is unable to deal with it either. Is this a viable solution if you have a lot of junior mid-level admins to do full, like, idempotent deployments of physical and virtual Linux boxes using everything from Rocky to Ubuntu and more, and to do this in a way that doesn't get management to say, enough, stop the line events because your thing broke, and stop doing that?
Yeah. I mean, you still need tools to manage your whole fleet, environment of machines, et cetera, right? And those tools are still going to be complicated.
Yeah, that'd be Ansible or something like
yeah.
that. But I'm just talking about for the deployment part.
Right, for the deployment, yes.
Because the Ansible part works really well. It's just the deployment part is really poor.
Yeah, and this can make that a lot simpler, right? I mean, I can't necessarily say what they're doing with RHEL because that's a supported product pipeline, and they tend to be very conservative about changes to deployment there.
Well, but Rocky is impacted by that.
But if you're using one of the upstream versions, then yeah, you can use something completely different and use Ansible. And like I said, again, once we resolve a couple of these issues, having the shim OS, which will not vary, which will only vary by machine as far as the hardware is concerned, right, is going to make things much simpler for a junior sysadmin.
Hi, Josh. You said bootc containers are also containers.
Yeah.
So you can just run the runtime and use whatever the host kernel is. Does that mean that there are limitations to what kernel you can put in bootc containers? Are they limited to Linux kernels, or are they? Can I run another operating system as a bootc container?
I would say theoretically yes. The trick is that you need somebody in one of those other operating systems to create a master bootc image for it. There's nothing that would prevent you from running FreeBSD or Nix. Well, I don't know that much about Nix's architecture, but theoretically there's nothing that would prevent you from creating a bootc image for those. I just don't know that anybody's done it yet.
Are there issues with doing this on a physical system with UEFI secure boot enabled, like signing of the kernel and things?
Yeah. It's more complicated. The config is more complicated because you need to do all the UEF and all of the signing and everything else, but that is supported, right? Because part of this is, like, the reason why my employer has put a bunch of engineers on this, in addition to the community folks, is that this is all supported through RHEL 10, and as a result, they were not going to push RHEL without having secure boot. So that's all supported. It's just that the upfront configuration, if you're doing an upstream distribution, the upfront configuration for you, because you need to actually check the signature authority and everything else, it's going to be a much longer config toml file.
When you rolled back, I was wondering if on reboot it's just going to go to the latest, or is there a mechanism for, no, stay at what I tell you to? And is there a mechanism for, say you have a set of VMs or hardware that you says like, no, this should always be on the latest major release or something. Is there any mechanisms for that?
Yeah. So we're talking two different things. For rollback, right, normally rollback just goes to the last good version that was booted, right? You see that rollback version tag. You can manipulate that, particularly if you've changed the system already to keep more than one version in reserve, right? By default out of the box, Bootsy only keeps one version in reserve, so you don't have a choice. But you can change that configuration to have more than one version in reserve and then actually pick. For updates, right, again, by default, it's going to look for that latest tag, but you could tell it to pull a specific image instead. And then that would be up to your automation to handle that instead of just using the defaults.
All right, my question is this. So I see you have it on your laptop and for a server someday, but what happens if I need persistent data? Does this format the disk to make a space for the images, or does it run in memory? And if so, like, how do I keep data persistent through this?
It only formats the disk when I first did the install. After that, it's only changing the places, the file systems that Bootsy covers. One of the things that it does change is if you want persistent data, you can't just stick it anywhere you want, right? There's specific portions of the Linux file tree. So the var, direct var, temp, any additional roots that you add, right? So don't stick any persistent data in user or bin, because those will get overwritten. But for other base directories, you can stick persistent data in those because those will not be overwritten by the image. And we've got, actually, this guy at the end has been really patient. Okay, it was the same question. Got it.
So can you do this with, without a hard drive? Can I run this just in memory?
So the question was, can you do this without a hard drive? Can you run this in memory? I don't see why not. I mean, you'd create a virtual file system and then install to the virtual file system, right? So I don't see why that wouldn't work. Haven't tried it.
So I work in a regulated industry that mandates a particular file system layout, like separate partitions for var and var log and audit and all that. How do you configure that with Bootsy?
Okay. That's not something I've contended with. That might actually end up being a problem for you, as in if they've stuck things in directories that Bootsy considers to be a part of the Bootsy image, then you might honestly need your own fork of Bootsy. I don't know that there's any way. Laura, do you know any way to configure that, like at runtime?
I know you can do symlinking. For reference, like you can symlink from, sorry. You can actually do some symlinking from the var directory to those directories to be able to write there, and then that var directory won't change. The actual underlying project that you would want to look at to understand how it works is called OS tree. There's also ComposeFS, depending on which system you're actually running. I think the Universal Blue family is all on ComposeFS right now. But OS tree itself is underlying the Fedora-based ones. So just for a clarification there. And there's a lot of information on those two as well. Current Fedora does have ComposeFS, but I think still running on OS tree until Fedora 44. Thank you.
One of the things that got brought up was that you're using your target device is x86, and so you didn't have to cross-compile. I understand how cross-compiling could be added, but for the part where you're able to run it outside of Bootsy just as a normal container, do you know what's involved in doing that? So like if you had cross-compiled and you have a Raspberry Pi application, you want to try that from your computer?
Yeah, I don't, because I don't do a lot of multi-arch stuff. Dave, if somebody wants to run an ARM container for testing on their laptop, how would they do that? Okay. Yeah? Yeah.
Quemu can do it because you can always just run like a virtualized Arch environment to test your Arch image. It's slower, but it works. Yeah, it absolutely is a huge performance hit for doing that, but you can do it. Otherwise, just have multiple bits of hardware for your tests.
Yeah.
I did have one question about bootc direction.
Yeah?
You demonstrated the soft reboot feature for just restarting user space and leaving the running
Yeah.
kernel up. Are there any plans to get that hooked up into different desktop environments so they automatically do it when possible?
I don't know. I don't actually know what it's doing now in terms of reboot.
Okay.
I haven't really paid attention. It might, like Bluefin might already be doing a soft reboot. I haven't checked.
I can confirm they are, but it would be really nice if they did add it.
Yeah, okay.
Thank you.
Yeah. I would say the person to ask that question to is George Castro, who is somewhere here at the conference.
So you can still use bind mounts and volumes like any Docker container, that's correct? Yep.
Yeah.
So that's
Yeah.
the answer to what was asked before about
Yeah,
persistent data.
you just want to take some care into what file tree you put those bind mounts into,
Right.
or use symlinks.
Yeah.
Any other questions? We have time for one or two more, I think. Okay, then please join me in a round of applause for Josh.
You're welcome.
Yeah, okay. Check, check, check.
So you said any way I do it is fine. You said UC Numalin?
Yep. Yep. Think of it like YUSSI. Yeah. I hate Google Slides.
Well, we don't have a rule here forcing you to do it. You want to put it up to something else. It is readable, I can tell you. You've got an hour to hold up these warnings towards the end if needed.
Yeah.
If you're already obviously at the end, I won't bother.
Yeah. I might not be able to take the full hour, but let's see. It really depends quite a bit on the demo also, how it goes and how well everything works. And
We're still 1 minute early before we get started, but I'll just give a few safety announcements since we are in potential earthquake territory, and hopefully we don't have fires, but there are exits both here and at the back where you came in. If somebody in the room gets really excited over this great presentation and needs the defibrillator, it turns out it's right on the opposite wall as you go out the door and to my left about 15 feet. Hopefully we won't do that. And if anybody should feel unsafe at any time during the SCaLE conference, we take that seriously. There's contact information on signs throughout the venue, but there is one definitely taped to that back door with the contact should you feel unsafe at any time during this conference.
could you grab a couple of photos? Sure. And then share later on.
Okay, I think it's time. I'd like to welcome you to the Cloud Native track at SCaLE. Our speaker today is UC Numalin, who's going to talk about pushing Kubernetes to the far edge. He is an authority on that subject. He's a senior principal engineer with Mirantis, working on the K0 project. Take it away.
Thanks.
Oh, and can you withhold questions to the end, preferably, and raise your hand, and I'll bring the microphone.
All right. I'm not really sure if I'm the authority on these topics, but I know a thing or two, but, you know, let's see. Yeah, so I'm Jussi, and today I'm going to share some information, knowledge, tidbits, experiences, learnings, the hard way, about how to push Kubernetes to the far edge. And of course, that relates to things like IoT, AI inferencing, and those sort of things. And I think today I'll actually going to try to spend quite a bit of time on kind of architectural patterns and how we can architect our Kubernetes environments so that they fit hopefully better into these far edge and like setups. And of course my clicker died too. everything is, computers are against me today, or electronics are against me today. All right, so of course we will first define what is far edge, at least in the context of this talk. Then a couple of words about why Kubernetes in the first place in these sort of environments, architectural patterns, and then how our K0's open source distro fits into the picture. I do want to introduce also to another CNCF project which is about resource discovery at the edge. How do we discover what's kind of beyond the edge computing, like IoT sensors and things like that. I do have an actual demo sample architecture, so please all pray for the demo gods. And hopefully in the end we'll have some Q&A time and let's see how it goes. Yes, there will be a live demo. I do have my Raspberry Pi here with me, and let's see whether it wants to work. I have a fancy AI hat on it, and the PCI cable actually broke down while it travels, so we have to suffice with CPU-only models for now. Yeah, let's have a quick look what is edge and what I mean with far edge in the context of this talk. Edge is one of those kind of hard terms in a way that if you talk to 10 different people about edge, you might actually get 10 different definitions what is edge. So there's it's not like mathematics in a way that you have one single answer for things. You have different views. But I think if we think about like your traditional centralized data centers, cloud provider environments, and then you go to further away from the internet, so to say, and towards the actual data source, real life data sources like IoT sensors and those sort of things. So gradually we move towards the edge of the network in a way. And while we move away from the big data centers, cloud environments towards the edge, our resource constraints go a lot smaller, right? You don't have, on edge, you don't have the luxury of spinning up 100 AWS instances up just for fun, right? Because your hardware at the edge will be super constrained. Also, what I've seen in real life is that the software stacks running on those devices will become more and more, looking for the polite word here, let's call them weird. So when you go towards like IoT environments in factories, the hardware and software stacks you're going to see are very custom made for that purpose. So you cannot take your standard Ubuntu packages and just shove them in a PLC controller. It's just not going to work. They are very custom made things, both in hardware and software. On the networking side of things, our constraints also go harder in a way when we move towards the edge. We're going to have lot worse latencies in our network, and there's going to be a lot more disruptions in the network. So especially in the networking side of things, nothing in the edge is stable, unfortunately. Like, for example, in my demo setup, I'm connecting the Pi to internet through my OS X, and it's very flaky. If you've ever done it with OS X, it's actually very flaky. But it's kind of a good in the context of this talk because, you know, that's edge. And then also, from the security point of view, our security posture goes a lot weaker in a way. Because not only you have to think about your software stack and the security of that, security of your communications on all different levels, TLS connections and those sort of things, but we also have to now start to think about things like actual physical security of things. So you cannot have your Raspberry Pi or whatever compute device you use, you cannot have it really physically accessible. Or if you have it physically accessible, you have to still secure it somehow, right? And this is where I personally draw the far edge. So it's really the smart device edge connecting to the actual kind of physical world in a way, to IoTs, different like IoT sensors, security cameras, and those sort of things. So that's my definition of far edge. It might differ from other people's definition, but that's how I see it personally. So like I said, we're talking about environment where the infrastructure and the device
microphone, right?
Yeah, but I'll need my hands for the demo, so we can.
I'll run down and see if I can get a battery.
Okay. Right. I think that actually summarizes my whole day today, so we're definitely living on the edge. So yeah, we're talking about infrastructure and devices located at the furthest edges of the network, and more importantly, they are positioned as close as possible either to the users of your system or to the data sources where you actually have to process the data. So when we think about those sort of environments, there's a few different problems that we need to figure out how to solve. Fleet management. How do we manage all those hundreds, thousands, tens of thousands of different devices? How do we manage our applications, whatever your application might be? How do you manage those across various different network sites, various different physical locations, and so on? How do we observe things, both the system at large, individual applications, networking, and all that stuff. Let's call it stuff. And then one critical aspect is also how do you operate your system? So
sorry about that.
check. All right. That's a lot easier this way. Sorry about that. So how do we operate the system at large? Can you or should you be able to really operate it remotely? Or do you actually have to rely on some human person to go on site to fix stuff? So, and of course, being good engineers, we need to think of solutions, what kind of technologies to use to solve these problems. And why Kubernetes? Well, I guess the obvious answer is that we were in a cloud native track, so we all love it so much that we want to push it to any single device we can get our hands on, right? But Kubernetes actually gives quite a lot of answers. It doesn't solve all those problems, but it gives quite a lot of answers to many of the problems. We get workload portability. So you can actually use Kubernetes to orchestrate your workloads across those different hundreds, thousands, edge devices, right? You have the best thing in Kubernetes, which is declarative state management. So you as an operator, you declare your state where you want to be, and then eventually the edge will implement that state for you, right? Remember, Kubernetes is an eventually consistent system. The eventuality might be in infinity at points in time, but it is an eventually consistent system. And I think one of the biggest drivers today is actually the CNCF landscape. Think of how big and wide the CNCF landscape is today. So you'll actually find a lot of tools, a lot of best practices already around Kubernetes. If I'd set up edge devices in a very custom-made way, what if I want to do something like service mesh? I'd have very, very tough time to implement that without Kubernetes and containers and all the kind of power that the platform gives me. I'm not a fan of service mesh, but that's just one example. And there's, like I said, there's a lot of practices out there for CI/CD and those sort of things around Kubernetes. All right. Let's dive into some of the architectural patterns that we can use when thinking of pushing Kubernetes to the edge. Of course, as architecture in general, there's no one solution. There's no right or wrong answer on things. So I'm going to present a few different alternatives. There's others. Unfortunately, you have to be the judge what is best for your use case and requirements and operability models. And it really boils down to kind of architectural requirements too, whether you want to have like every single edge site, is it going to be the same as all other sites, or are there variants between your edge sites? Do you want to run less clusters or more clusters? Because managing one or handful of clusters, that's easy, right? That's Sunday afternoon. But then 1,000+ clusters, that's a systems engineering problem already, right? And then, as always, it really boils down also quite a lot on the fact that what resources do you have available at the edge? Do you have the luxury of actual servers at the edge sites, or are you running like Raspberry Pis? Okay, it's working. It did some beep. Or are you running Raspberry Pi or Pi-sized devices at your edge? Because that's going to give you a lot of constraints. One very common pattern that I've seen and heard is to have independent clusters at each edge site, each location. What I mean by that is that on site A, you have one or more independent clusters. So independent here really meaning that the cluster is fully located at the edge site. Both the control plane and the worker plane, everything is located at the edge. And when we're talking about edge, I mean physically located at the edge. Of course, different sites have different clusters. And now if you scale, you have 100 sites, you end up having 100 clusters. And you have 100 control planes to manage and 100 etcd clusters to manage at a remote edge site. So again, I guess you can pick up that this would definitely not be my favorite pattern to use. I'm not a fan of etcd. The pros of this approach is that the clusters are very resilient from networking point of view now, because there's no connectivity between the, say, internet and the edge site. I mean, of course, there's probably connectivity, but from the cluster operations point of view, we don't need any connectivity. Our failure domain is very natural now, because everything is physically located at the site, right? Data is local. Both the Kubernetes state, the declarative state, is within the site, and also the actual real-world, say, IoT data is also local at the site. So the cluster is sort of autonomous in a way. The bad side of things is then the fleet management problem, because you will end up having hundreds of clusters to manage. You have to figure out things that, how do you back up a site? How do you restore a site? How do you build your observability in a way that the site might be without network for days? And if that's the case, how do you operate it? Well, probably the last resort is always to send someone in, but whether that's possible, I don't know. The obvious concern is also the resource needs, because we're going to run control plane nodes there too, which I'm sure you all know, they are huge resource hogs. kubeAPI server and etcd together will eat all your RAM that you have available, more or less. Another pattern that I've seen around is what I call single node clusters, meaning that a single node, a single Raspberry Pi device is actually both the controller and a worker at the same time. Then each of your edge site might actually run X number of these setups, meaning that each of the devices are really, really autonomous in a way. I heard one example of this use case where they actually run this sort of setup on cable, what's the word here? Set-top boxes on cable. So when you have in your living room, you have the set-top box, it actually might be running a single node Kubernetes cluster for reasons, I guess. Don't have any actual details on that case, but I just heard that someone is actually doing it. The footprint is, of course, sort of minimal, because everything is in a single device, a single node. Operationally, it's super simple, because you don't have etcd, HA problems. You don't have to figure out any availability things, because you've designed it to be a single node, so it is a single node, both in good and bad. Data is still local. Operationally, it's kind of autonomous. Of course, it is a single point of failure, because we designed it to be a single point of failure. We still have to figure out backups per site. Data storage might be a problem now. And again, the observability and operability are a bit of a challenge. Again, because if your network is broken between you and the edge site, you have zero means to observe anything, or operate anything. Third pattern is what I call centralized control planes. So turns out that with Kubernetes, you don't actually need to run the control plane and a worker plane next to each other. So what we actually can do is we can sort of externalize the control plane fully out of the cluster. What I mean by fully out of the cluster, I mean, of course, worker plane and control plane, they are always connected one way or another, right? But the control plane node, they don't actually have to run any workloads. You don't have to run kubelet on a controller node. You don't have to run containerd on a controller node, which means that you're not going to have to run CNI on a controller node. Because it's basically it's CNI that forces you to run everything in a kind of flat-ish network. What this means is that basically my edge sites will run pure slim worker nodes now, which are, as we know, a lot easier to manage because there's no etcd and other nasty bits involved. And you can scale your sites depending on how many workers you need on site A or site B or D or whatever. So some of the pros and cons for this approach is on the positive side, the control plane operability is a lot easier now. You can actually operate with the control plane even if the edge site are without a network. I can still talk to the control plane with kubectl. I can see what was the last known state. I can see some observations, what were the last known observations. And I can even do kubectl apply. I mean, it probably won't have any effect yet, but it will take effect next time the site connects to the control plane. Data is still always local to the edge sites because the workers are the ones processing the data. So we still have the data locality at the edge site. Your multi-cluster user experience is a lot better in a way because you can manage the control planes in the same exact way regardless of to which site that control plane belongs to. So let's take a maybe a bit stupid but practical example. You could have an Amazon EC2 instance running control plane for site A. Now you can basically clone that to run control plane for site B. So meaning your operational model for the control plane is a lot easier that way. The bad side of things is that the wide area network is now actually part of our control loop. What I mean by that is that if my site loses a connection completely, I will not be able to push any changes to the site because kubelet is not able to pick up the new data from the control plane. Data storage might be here, but data storage is always an issue in Edge, unfortunately. The blast radius is kind of a 50-50 because it's also pro and it's also a con. What I mean by that is that on a let's look at it from the positive side first. The blast radius is still kind of natural in a way, because if we think about cluster as a logical entity, I have a dedicated cluster for site A, but now I'm separating the control plane and the worker plane, so the blast radius is actually kind of mixed in a way. And then, depending on how you set up the control planes, you might end up having more blast radius. So say I run all my control planes on AWS US East 1, I know that's a bad idea. But if I run it on one region only, and that region goes down, as we know it tends to do, I lose all my control planes, more or less. Or at least you lose the operability of those control planes. You probably don't really lose them as such, but you get the point. Right. But like I said, architecture is set of opinions. There's other possibilities or combinations of these, so feel free to mix and match and figure out the best way how do you operate your environment. How do we make these, or how do we support these sort of patterns in the K0s project, which is a CNCF sandbox project? So we've designed K0s in a way that it has a minimal possible footprint when running on the nodes. I'm not saying that it has a small footprint. It has a minimal possible footprint. Because with K0s, what you get is Kubernetes. So there's like, our hands are kind of tied a bit there. We try to make the operability as easy as possible. We package everything into one single binary file, which is pretty simple to operate, right? I drop the binary on my server, I run it, and now my server is a Kubernetes node. I didn't have any dependencies to install. I didn't have to figure out how do I install kubelet package on my super old DPN box or whatever. It's statically compiled, so there's actually 0 dependencies. And why that makes operability easier? Well, when I have to upgrade my Kubernetes node, I put new version of the binary in, restart the unit, and boom, my upgrade is done. Of course, we all know that upgrade with Kubernetes is actually, well, you can do it that way, but you probably would want to drain your nodes and all that fancy stuff, but you can actually do a K0s node upgrade that easily. One of the kind of cool bits, especially in these edge-like environments, is that we've actually built in a component that what we call autopilot. The autopilot component can actually upgrade the cluster itself. So it's a component running within the cluster, and it can orchestrate a full cluster upgrade by itself. It does all the things that you would typically do in an upgrade. Upgrades all the controllers first, one by one, to ensure availability, then moves on to the worker nodes, starts to update one node, drains workload out of it, replaces the K0s binary, restarts itself, and then moves on to the next worker node. And we also have few optimization flags for these single node setups. So you can actually run K0s controller -- single, which will run a simplified control plane. By simplified, I mean we don't run etcd in that special case, because we don't need etcd for a single node case. So it actually automatically replaces etcd with local SQLite database. In K0's day 0, when we started the project, we did this architectural decision, what we call control plane isolation. The fact that I mentioned earlier that Kubernetes doesn't actually force you to run workloads and kubelets and all that stuff in control planes. So that gives us a couple of things. There's no way for me to schedule workloads on the controller nodes, either on purpose or by accident. And then it really allows a lot more flexibility on our placement strategies for the controller nodes. In Kubernetes, we do actually need connectivity between control plane and a worker node. So basically, when you do things like kubectl exec, kubectl logs, API server actually calls kubelet API to get the data. So we need to still cater for that communication. For that, we actually utilize sort of reverse tunnels. So in an example where I have edge site somewhere far away from my control plane, it's actually the edge node calling home to the controller node and opening a tunnel. Think of it like a reverse SSH tunnel in a way. It's not implemented on SSH. It's conceptually exactly the same. And then when API server needs to connect to kubelet, it goes through this tunnel. So especially handy for these edge-like setups where you probably have layers and layers of firewalls and NATs and whatnot in the network. As long as the worker can call home, your Kubernetes cluster works as expected. Right. All right. Let's move on to a practical example. So my sample application is as sample applications always are, simple and stupid. So my goal is to recognize objects from video feed. Think of like home security system or something along those lines. I have my edge node that I want to connect to a video feed. All the data has to be processed locally and locally only, and have an AI model doing the actual object detection, also running locally at the edge, or AI. To make things fun and to introduce another CNCF project, I'm in the demo application or demo architecture, I'm using a component or project called Acri. So Acri really is a project for IoT and IoT-like device discoveries. So if you think about edge, your typical use cases are IoT and IoT-like use cases. And what we want to do and what we need to do is kind of connect our Kubernetes cluster to the world around it in a way. So what Acri actually can do is it can discover the surrounding devices from your node. Devices like IoT sensors, video cameras, whether they are USB like in my setup or whether you have a network video feed on this, what's the protocol called, ONVIF or something like that. it exposes those found devices as Kubernetes resources, which means that I can actually use those devices now as scheduling constraints on my pods. So in my application, I can tell that, wait a minute, this application needs to run on a node which has this sort of device available, like you would do for memory or AI or whatever. So with Acri, you basically give it a configuration object. You configure a discovery handler. Say that you want to discover like all the on-with video feeds on your network or UDEV devices like in my setup. For every device it finds, it actually creates this instance object telling that, okay, I found this device on this node, through this node, and it has these properties available. One of the super cool things with Acri is that it can also automatically deploy brokers. And a broker is basically, as the name implies, something that brokers between your application and the actual device. So in my example, because I'm using USB camera, I'm using the UDEV device discovery. So what Acri actually does, it automatically deploys a broker pod on the same node. Well, I have a single node, but on the same node, I have the USB camera attached. And what the broker actually does, it gives me a gRPC interface to the frames. So my application doesn't actually have to even know that how do I access camera on a USB. I don't know how to actually do it. There's probably some cool library to do it. But now I can just call a standardized gRPC service to get a frame. Or it could be some IoT device. And then Acri, I think for many IoT devices, it actually deploys an MQTT pod to broker the data, which is super cool. So this is basically my sample architecture. I have my mothership cluster. Remember I said that the control plane is externalized. And now control plane is not running containers or kubelet containerd or anything. So my control plane is actually running as a pod in a mothership cluster. That's actually a cool pattern. And my team also has a project called Cosmotron to facilitate that stuff, which is also a CNCF project. So control plane running on cloud. My single site is my Raspberry Pi here locally, connecting to world around it. Well, the camera only, unfortunately. So Raspberry Pi, I do have an AI hat on it. I use the Halo AI hat. Unfortunately, I got to mention that all the Halo stuff is unfortunately not open source, which makes it pretty, excuse my French, but pain in the ass to actually set up. I was running YOLO V8 from the Halo Model Zoo, but the PCI cable decided to go bust on me while my travels. So I'm actually not going to be able to run anything on this Halo hat now. I do have a sample application running on plain CPU, but you can imagine that it's not that fast, right? But you'll get the point of the architecture and stuff anyways. So basically, my application running in pod is talking to the Acri broker, to gRPC, getting the frames from the USB camera, and then it feeds it to the YOLO model for object detection, and then shows us the output. Right. Is the font big enough? All right. kubectl get node. So single Raspberry Pi, as expected. And don't worry, I'm not recording anything, so. Get configuration. So this is the Acri configuration object. So what I'm basically telling here is that we use the udev discovery handler, and then I'm basically telling the rules that, okay, look for video devices on the kernel, and that's about it. In the configuration, I already tell that if you find devices on a node, deploy this Procore pod on the same nodes, so that I get the fancy gRPC automated interface for me automatically. And now for the actual instances. So let me put it up there. So Acri found an instance of a device using the udev configuration on a node, Raspberry Pi 5 local, 3 hours ago. Wait a minute, I booted it up like less than an hour ago. Maybe it has. Maybe it had the object already in the API, probably. Okay. And now for the actual demo application. I have a deployment, detector demo, SCaLE deploy detector demo. Oh. Replicas 1. I'm not running it all the time because, you know, I don't have even a fan on my Pi, so it would probably turn down something. And to be able to access it, I did already expose the service as a node port service, kubectl get service, and the port is what, 31. This is actually, I mean, I'm by all means, I'm no expert on any AI stuff or models or whatnot. But when I started to put this demo application together, I got actually surprised in a way that that just with Raspberry Pi and a plain CPU, I can actually get a decent frame rate. I mean, it's not like you would do any gaming with that frame rate or anything, but there's probably a lot of use cases where that's actually enough. And my application is probably doing a lot of stupid things too, so you could probably optimize the hell out of it and get a lot more frames. When I did the Halo AI hat version of the application, I was able to get like 20 frames per second. So it's actually quite a big increase just by adding a dedicated processor for the AI model stuff. But of course, your mileage varies depending on what you're actually doing, what kind of models are you using, and how do you do the inferencing. mine has been working with a non-profit organization where they've taken this exact same architectural pattern to the extreme. So they've actually developed this underwater buoy of sorts, which is analyzing the natural habitat of coral reefs. So basically the environmental conditions on coral reefs. It's actually running Raspberry Pi. And the Pi is a single worker node connected to control plane running somewhere else. There's a QR code to the much longer blog post going into the details what they actually do and so on. But I think that as an example of edge deployment, that's kind of like you can't really go much further than that. I mean, if you go further than that, then we're out of the planet already, probably, right? But that's super cool use case. So, as a summary, there's a lot of use cases on edge to run workloads and AI workloads. Think of like smart cities, industrial automation, retail stores, and even underwater for things. Kubernetes can work in these sort of setups and architectures, but you really have to think what's your operational model. Do you want to separate the control plane, worker plane? Do you want to run single node clusters at your edge? Do you want to do some even more fancy stretch setup? Or what fits your use case? With K0s and Acri, you saw a neat, nifty, simple-ish architecture. Thank you.
I think we've got time for some questions. Please raise your hand if you have one.
If you have the centralized control plane, does kubelet control its callback? So if you were trying to save resources, could you have kubelet decide, I only want to touch base once every hour?
No. Kubelet and pretty much all of the Kubernetes components that need to be in sync with the state, they're all implemented using the watch concept. So basically it's like a sort of a callback. So whenever something changes on the API server, it's immediate callback to kubelet. At least, yeah. I'm pretty sure that you cannot configure kubelet to do polling stuff.
Yeah, hi. I was wondering, you said that you couldn't run a control plane in AWS for Kubernetes in multiple regions, but can you make it redundant?
So of course you can run your control plane on multiple regions. You can do it, yes. But the problem is that the region-to-region traffic gets a bit slow. And in Kubernetes, when we talk about highly available control plane, we mean we need to have an etcd cluster. And etcd is super picky about the latencies between the nodes. So multi-region, I'd say no. I haven't actually tested, but I'd say that it probably won't work. Multi-AZ definitely works, that I know.
If you don't want it in multiple regions of the control plane, can you at least use like different nodes within one region in AWS? to make it a little more redundant?
Yeah, you can. You definitely can do and should do multi-AZ for your control planes. Absolutely. Yep. One thing I actually forgot to mention or actually add to the slides, because many times I get the question that what about latencies between the, even if the network is kind of up between the controller and worker, what about latencies? I've been actually testing, and I'm working on writing a blog post testing that how bad or my kind of idea or premise for the blog is that how bad can I make the network before kubelet starts to throw up, basically. So far, I've been able to make 1.5 second latency and 50% packet loss, and kubelet is actually still happy. I mean, yeah, of course, it does mean delays from your kubectl applies to when actually things boot up, but does it matter? In most cases, no. But I was hoping to get the blog up to this event, but you know, time and life happens.
You said the latency for etcd between regions. How much of a latency can you have with etcd?
So etcd typically needs, I don't remember, they have official documentation about the latencies and stuff, but I always say that your typical node-to-node latency between etcd is max like 20 milliseconds or something.
20 milliseconds?
Yep.
Okay, thank you.
I think we have time for one more if anybody's got a question. Okay, could you join me in a round of applause for this presentation from Yusuf?
Thank you. Thank you.
It's pretty good timing. If you want a picture of yourself in front of the podium, I'll take it for you if you want to.
My friend took it already.
Okay. Thanks again. Good presentation. Sorry about your halo. How much do those?
I know it's weird because if I put the PCI cable in, it won't boot up at all.
It might be shorting something in that connector, but
Because
my guess is it may be fixable, but not in a hotel room with no tools.
Yeah, exactly. And I think, I mean, how much would these cost? Probably like 10 bucks.
Is it a replaceable cable on both ends? Yeah.
I can just plug it out here. So it's really like, if I get these from Temu or something, it's probably like 20 cents.
Yeah.
Right?
How much do those halos cost?
It's about, I paid like 120 euros, which is like around 100 bucks. But yeah, the part that
I'm running Frigate with image classification at home, but using the Coral.
Yeah.
I've heard these halos are better though.
Yeah. I mean, it's pretty okay. I mean, with a setup like this, when I can get like 20 frames per second, it's pretty okay. And I could probably go a lot better than that by fine-tuning some of the application and testing the various different models and their parameters.
Most of those image recognition use cases, though, you don't even need the 20 frames a second, right?
Exactly.
I mean,
Exactly.
Really, 4 or 5 will work.
Yeah. So you don't probably even need the AI hat.
Right.
Yeah. Which actually means that I can power this with the power bank.
Well, you know, I think the image classification use cases that kind of need the accelerator is, it's one thing to recognize the person, but then if you want to compare it against an inventory of people, or if you wanted to do OCR, like you're capturing car license plates but you want to actually OCR those to get those into something, because you don't really want to send the raw picture to be actionable, right? You really, from edge, if it's a car, you want to deduce it to the license plate. If it's a person, you'd like to have that mapping to a name or a recognized individual occur out at the edge. And then I think that's where you probably need the accelerator, because you're doing it. It's not YOLO anymore. It's YOLO to get the fact that it's a person, but then it's a second pass to get the...
Exactly. But then comes the architecture again in the picture that you know, you probably want to do that sort of lightweight detection at the edge. And then when you recognize that, okay, this is a car that was speeding or something, then send that frame out to cloud for actual processing.
Maybe. There's a lot where maybe you don't, but I mean, if it's a privacy issue, you might actually still be precluded from sending it out to cloud.
That's true. That's definitely true. Yeah. That's true. But you can do a lot with these small devices nowadays.
Yeah, and it's getting better. I mean, the interesting thing, I'm in the CNCF, I'm co-chair of the IoT Edge working group. And the interesting thing...
I have a link to that.
Okay. It's sort of dying off because a lot of that has gone into AI-centric because the AI has just eclipsed the interest level of...
It's eating anything and everything now.
Yeah, but all of the people making embedded processors now, and I do mean all of them, they're bundling it with inference engines. They're not like general purpose AI accelerators, but the fact is you don't and shouldn't be doing training out at the edge. You should only be doing, you know...
It's inferencing always.
Right.
I mean, I've never heard a use case where people would even think of doing training at the edge.
Yeah.
I mean, they...
You do that once.
Huh?
You only do that once.
Well, in fact, if
Then you get to wait.
you take the penalty of moving all the data, but you don't even have to do it once, really. As long as you have the bandwidth to move some of these things up to the cloud to run it there where... because the fact is it's going to be way more efficient to do it with rented GPUs because the training is typically, you know, something, it's a temporary step. Or maybe you repeat it once a year, but you don't need to sink all that capital into enough to do training when you're only going to do it incidentally. But the fact of doing it in a cloud does make sense for training because if you've got the distributed edge scenario, like say I've got traffic cameras out at 10,000 locations, you obviously can't train it effectively at any one of them because they don't even have the data amassed. You need to move that up somewhere, but you're in no great hurry either. So you can kind of opportunistically manage to collect that data, do the training, get improved inference models that you then push back down to the edge. And I think that's the way it should, and that's the way people are doing it.
Yeah.
So, did you see the presentation before you?
Nope.
Do you know about Bootsy? Do you use Bootsy?
I know about Bootsy, yes.
It seemed to be
It's a cool thing. It's kind of one of those things on my to-do list to get my hands on. But the problem in my life is that list only gets longer.
Yeah. As a general principle, I mean, Bootsy is one way to take advantage that the OCA packaging format is actually very flexible. And for Edge, really, for practical implementations, you know, for redundancy and resiliency, you probably already need to keep image registries out towards the edge too, because, you know, if you can't do that for a lot of these use cases, then you're dead anyway.
The local net might still be there.
But there have been other presentations at SCaLE. There was one a couple years ago. The guy did it under the auspices of secure compute, but it was the same thing, bundling an OS image with the actual container or containers that would be hosted on top of the OS. And it was targeted not at an edge use case, because he was talking about doing it for these things called enclaves. There's a whole concept of security. With on the Xeon processors from Intel, they actually are encrypting even at runtime. So theoretically, you could have a cloud provider like AWS hosted, but even if there was a tainted administrator, he can't actually get the real data because it's actually locked in the enclave on the CPUs and encrypted. And short of doing things like drilling into the chip to get signals off of memory buses, after it's been encrypted, you can't get at the stuff.
I understand there's a plugin that goes in between the RAM and it can, on the fly.
Well, the DRAM maybe, but then the cache on the chip, which is what the CPU actually consumes, if that's where your decryption point is, that becomes a lot more secure. Anyway, I wasn't advocating that as a role in Edge, at least so far, because nobody has these enclave chips. It would be great on the Edge, given that it's an insecure. Well, there's probably a market for it, given that one of the unsolved problems of Edge is there's no physical security. So you put these things out there, and they're pretty much unattended. People can either steal it or worse, taint it.
A colleague of mine is working on a demo where we run basically the same setup that I had, but the node is actually running in fully diskless mode. So everything out of memory. Which means that if someone goes in and takes my device, they have to unplug it, which means that everything is lost.
Yeah.
There is a really easy solution to that. It's called contractors adhesive.
Sorry, what?
Contractors adhesive. You put the device and it stays.
Ah, yeah.
Well, for a lot of these things with finance involved, completely stealing the device isn't actually your worst case. It's actually tampering with it and leaving it in place so you don't even know that it's been compromised.
And it's compromising the data flow. Well, thank you very much. I look forward to having the smartest sprinkler system on the block.
Really?
Yeah, I think
My goal for the past year and a half has been to build kind of on top of this architecture, build a kind of sort of a security, on the other hand, nature watching system on my summer cabin.
Oh, okay. Yeah, you want to keep track of any bears that they get inside.
Yeah. Or general animals that come to the property and those sort of things. Basically, the idea has been to use the YOLO and other models locally to pick up whether there's any like activity in general.
Yeah.
And then feed it into some other.
It's a deer or
Yeah. Yeah. Then do it in stages in a way that first detection is like whether there's activity of sorts, and then second one would be to actually figure out which animal was it. Yeah. And then if it's a bird, then third model specialized in kinds of birds that okay, what kind of bird was it?
So I went down the path. I've had the Frigate NVR running at home for security. It's a different use case than animals. It worked. I'm happy with it. It's still there. But then, decided I need cameras anyway. There was some sale on those TP-Link topos, and they have a line that's all solar charge. Because one of the big things with putting it at these places is, running wire and not just the signal wiring, because you could arguably use Wi-Fi, but you still have to power it. But those actually have a little solar panel, and they actually go into a deep sleep. So they actually use kind of a conventional motion detection. They don't say what it is, but I suspect it's kind of like infrared or something. In fact, it must be, because it works even at night.
Yep.
And then it wakes up only when something is there.
Yep.
And it actually seems quite reliable. I mean, it's detecting smaller animals. Like it actually detected once a spider that was crawling across the lens, arguably, but it clearly detects dogs and cats. It was a big one because it's Southern California, so like they literally have tarantulas here.
I'm ready for my
But anyway, they're called topos, and I got it on some sale, but it was less than $100 a camera with the battery and the solar panel. And
That was cheap.
and I thought when I was at that price point, it would be a piece of junk, but it wasn't. And then I went and bought 2 more of them.
Well, then, yeah, they match it.
I mean, I was even thinking, now this is in Southern California too, where I have the luxury of lots of sun. So I'm going, you know, these connect back via Wi-Fi, and that's actually a big power pig right there. And just getting enough current per day to keep a battery running that would, the Wi-Fi is going to burn like 100 milliwatts while it's active. But it's now been up for over 6 months, and through the winter, which would be the tougher season. And they work. They actually do battery monitoring, and it's never got below 95%.
So when you plug your Raspberry Pi in the next time you're working on it, does it go out and connect to your cluster automatically?
Yes. It's worker node. If I now look at the
Oh, I get it. It went yellow. The cluster
yeah,
ready.
if I now go kubectl like at nodes, I would see Raspberry Pi not ready.
But once it wakes up, i.e. you plug it back in, it connects and
Yeah.
is
It
happy.
pulls up the last state that it needs to run, and it's how Kubernetes is designed. And then if you think about what happens when if it would be now plugged in, I mean into power, and if I just yank the network cable, what happens? It keeps on running the last known state until it knows that anything else.
Waiting to connect again.
Yeah. Yeah.
Yeah, some of the people brought up the issue of, you know, like these stretch clusters over large domains with big network latencies. But actually, I think once you start going there to try to use Kubernetes to manage edge at scale, I think the bigger problem is just the node scale up that, you know, getting up there to literally thousands of nodes, which is not unusual in edge, especially 10,000. That's kind of beyond the initial early days of Kubernetes. Just didn't imagine you would take a Kubernetes cluster that big. And I can't say that I've kept tabs, but it is quite a challenge to where one of the aspects of those gigantic cluster node counts is that you need a bigger and bigger etcd installation, and it gets really prohibitive. And I've heard of places that tried to go there and ended up with AWS bills just for hosting their etcd that were in the hundreds of thousands of dollars a year.
There's a blog from was it? I want to say Google, but I'm definitely not sure. But anyway, there was a blog post where some group of people took it to the extreme, and they have like 100,000 nodes in a cluster.
Yeah.
But they had to do very, very nasty tricks to the
Yeah,
control
and like I
plane
say, the cost of keeping that etcd cluster is so enormous. You know, your fallback then is you don't manage the whole world and you break it into regions, and that might work for some things. But, you know, some of these edge applications, like whole automotive fleets, like BMW wants every car in the world for management of firmware updates. That's going to be millions of nodes if you went kind of this.
Oh, does it fit?
It doesn't. It doesn't.
Oh,
That's why I have rubber bands.
I was thinking.
And that's why probably the cable broke down.
3D printer.
Yeah. But, I mean, that would be really cool if it fit with a hat.
Yeah.
Yeah, I think the Kubernetes people, I mean, once they got hit by, oh, it's stable, now it's, what do you mean you want 10,000?
Well, there's interesting projects like that Josh in the prior presentation mentioned, the Cubestone. I don't think it's getting a lot of traction, but it's an interesting concept where it's a hierarchy of Kubernetes clusters, and then it's one of the reasons that it's so costly at scale is you're sending massive amounts of this stuff down. They effectively are, the way Kubernetes works is you state of how you want the world to be. They're effectively compacting up at the upper tier cluster. And then at the lower ends, they can be as small as single node clusters. But they're not really the standard declarative things at that topmost cluster. It's just keeping a blob that it doesn't know about that's been compressed. Like imagine it's not literally PK zipped, but if you took the YAML specification or something and just squeezed it down to where it's as dense as carbon pressed into diamonds, that's what it's like. And it just knows that this is actually owned by my child cluster. It's going to be the authoritative thing in charge of actions on this. And you just push it down, and you have the illusion of centralized control because you can define all these things up there. But the things are tagged as this isn't really mine, so just compress this down and kick it down to the next level. And it's an interesting concept, and it's at this point that project's been out there a couple years. And I actually like the architecture of it. It makes sense for a solution to that, but
it's kind of like, I do like the architecture in a way, but then again, it's kind of a blunt way of doing things also in a sense. But I've seen also people use virtual kubelets in this space. So your virtual one kubelet is actually controlling a fleet of devices behind it, which Kubernetes sees as one node in a way that. But there's, like I mentioned, it's architecture, so there's possibilities, opinions, pros and cons, and
I think it's clear there's no centrally recognized right way to do this, but it is something that someday will get solved because there's enough demand for it. And it's only going to get worse as AI moves into the physical world. Well, the whole AI thing is going to actually create demand for compute out at the edge that you're going to want to manage. And not just the compute, like the images and whatever, the software delivery, but also the feeds of actionable data back. It's just like you captured that with the camera, but like you and I were discussing, you're not going to send frame-by-frame images for analysis up in the cloud. You actually need to compress that data down to small amounts and basically turn it into events. It may be events with supplemental things, like if the event was somebody broke a window, and I have a picture, the event is window broken, and then you attach the picture to it and send it up, and it's
you'll be able to look at the Prometheus metric to see, oh, the CPU is really busy. There must be something that it was looking at and doing. Thank you very much.
Thank you.
thank you.
Test, test, test. Hello.
Good afternoon, everyone. Our next speaker, John, will be discussing Apple's recently open source containerization framework, which allows you to use containers in an interesting way on your Mac. John is a software architect and a developer at Apple. A versatile software architect with a broad background and spanning web, mobile, and embedded systems and enterprise storage, and with a passion for elegant software. So, John Logan.
Silence my phone. Hi, everyone. Before we get started for real, I have the GitHub site up here. If you want to play around with container, I'll shortcut that, and you just go to the release page. And we just released 0.10 last week, and if you scroll down below all the text, you'll see a signed installer package there. It's like an Apple package installer package. You can download that, double-click it. You'll be prompted for your admin password because it has to put something under user local bin. But other than that, you should be good to go. And there's a couple of pages that you can try out if my computer will let me. So here we've got a docs directory, and there is a little bit of markdown. The ones that are probably worth doing first are the tutorial and the how-to. And then, of course, the README on the front page has a lot of the getting yourself up and running stuff. So with those preliminaries out of the way, we ready to go? Cool. All right, let's do this. See if I know how to run my Mac. Do that, do that. Okay. Good afternoon. I'm John Logan. I'm a developer on Apple's containerization team. and I'm happy to be here today to talk to you about our open source containerization projects. Last June, we open sourced the Apple Containerization Framework, and it allows you to build, run, and publish Linux container images on your Mac. And we did this with an approach that focuses on security and privacy. There are two key projects. There's Container, which is the tool. I just kind of talked to you about installing that, right? It's a tool written in Swift, and it's for managing containers. And if you've ever run any other tools like that, it's going to function very similarly to those sorts of tools. It'll feel pretty familiar. And then there's also Containerization, and that's the Swift library underneath that the container tool uses. The slightly awkward title to this talk alludes to the role of this containerization library. It's the basis for container, but you can also use it yourself to embed Linux containers in any Swift application that you write. So here's what we'll cover today. First, I'm going to set the stage with a brief overview of containers. And after that, we'll cover the design principles that we used as we built the containerization library. I'll demonstrate how you can add a subcommand to the container tool, how to extend it, as well as look at an application that, like I said, was built straight on top of containerization. So you're not running Podman or Docker or our tool. You've got it embedded in your application. I'll talk a little bit about why and how we did it in Swift. And finally, wrap up with a word about the open source community, how you can get involved, and a little bit about our goals and plans. Oops. There we go. Okay. And I didn't do the build-up. Okay. Let's start with what are containers. We'll start by framing what we mean by a Linux container. And there are a lot of ways to come at this. Some of them are more pedantic or technical than others. I'm going to look at it from two perspectives. A runtime perspective where we're looking at containers as a way of virtualizing applications so that they run securely and run privately. And then a second sort of view of it is as a packaging construct. It's a development workflow, containers as a development workflow for publishing and deploying your apps anywhere. Now, a key property of a container runtime is it virtualizes the application. It makes the application think like it's running on its own private hardware, and we say that this isolates the application from the underlying host. And it's done in a way so that it allows the application generally to run at full speed, but anything that could escape that container has to go through a checkpoint. Sort of a fuzzy definition. But this virtualization also implies that the applications are isolated from each other. And together, this means that applications run securely and that containers can't interfere with each other or with the host in any way. And also that they run privately, and that means the containers can't see what they shouldn't see in another container or on the host. Both of these properties are really crucial when you're deploying at scale, and especially crucial when you're deploying in a multi-tenant environment where you have customers, different customers that might be running on the same hardware. It's also important for local development, though, because containers allow we developers to rapidly create, run, and delete all kinds of dev environments without impact to your base system and without conflicting with each other. Okay. And the last thing that I want to think about when it comes to the runtime is performance. It's a final consideration for a developer, a container runtime. As a developer, we don't want to be waiting all day for commands to complete. So our container tool needed to start up and shut down containers efficiently and responsibly. And I'll talk a little bit about that in just a sec. So as far as packaging is concerned, let's talk about how we package and deploy applications. Let's imagine a server-side app that we could build directly on our host. Say a REST service that talks to a Postgres database. What's needed to run that app? Well, there's the application itself, like the code that you wrote, and that's often compiled in some way. And then there's everything that your app depends on. There's libraries. They might be compiled from source dependencies that have been pulled in, or they could be linked in statically or dynamically. You might need a language runtime, depending on your language. And you're probably going to need some data, content, assets, those sorts of things. If we're talking to a database, we might need an init script, for example. Now, if you're developing all this right on your Mac, you might have to install some third-party apps, or on an Apple system, you might have to install some homebrew packages. And you can put some of that setup in make files or scripts or eventually inconsistent README files. But the problem underneath all that is, how do you make it so that anyone can build your app, and even if they're not running the same type of OS or computer system as you? Well, containers give you a way to package all of that as a standard container image, created with a set of host-independent instructions. So what you do is you make a Docker file, and that Docker file pulls in a base image, installs some dependencies, builds and installs your app and your data and assets, and you might give it a command for it to run and an environment for it to run in. And that defines your container image. From there, you can build that image and test it and publish it on a registry once it's working so that it can run as a container anywhere. And in a nutshell, that's what containers are all about. It's running your applications in secure private isolation, and it's also an easy way to package and deploy applications to any kind of platform. Okay, so before we move on to the containerization library, I thought I'd just show the tool in action just a little bit. It's going to be a really simple demo. See if I can get this pivot done right. There we go. Okay. How's that? Is that, do I need to font up, or it's all right? Poco más? Yeah? Okay. We can do that. There's going to be some wrapping at this point. Oh, wait, that's not. Nope. Hang on. Okay. I work for Apple, and I don't know how to make a font bigger. What's that? Sorry, I missed that. Oh, okay. Oh, there it is. Okay. What's Command Plus? I thought I was doing that. Pretty big there. Okay. How's that? Good and back? Awesome. Okay. Yeah, I thought I made it large enough, but maybe not quite. Okay, so I kind of have all the commands we're going to run here. But so started today. I'm not running container right now, so I can run container. I can type it. Container system start. And what this is going to do is it's going to bring up a bunch of XPC services that get containers running. You see it starts pretty quick, and from there, you've got pretty much, you're managing resources, right? So container ls, oh, I have a thing already running, so we'll container stop web. Had one left over. There we go. Takes a second to shut down. Okay, so you can see I can list the container. I brought my image down already so that we don't have to worry about the network. I have a volume. We're not going to use it. And then you can create one or more networks. You get a default network here. You can see it's on this subnet. And then there are a couple other things. We keep track of registries for you. Oops. Let me just use search instead. Okay. And one interesting one is we allow you to create local DNS domains. So we run like a little local DNS server. And you can see I've created kind of the standard local domain test. And this is, you'll be able to see this in use here in just a sec. So those are all our resources. And what I've got here, if I look in my HTML directory, is just a simple, there we go. So you can see, just a simple HTML file, nothing fancy, okay? And then we run a container. So let's go through this command. It's a lot like a Docker command or a Podman command or Colima. container run. -D runs it in daemon mode, so it's going to run it in the background. RM is going to get rid of it after I'm done. I'm naming it web, and that's going to be important because it's going to apply my default domain test to it, so it'll have an address record of web.test. My working directory is user share HTML, and we're mounting in my local HTML directory into user share HTML in the container, running Python Slim, just a lightweight Python image, and starting up a dev web server. And one other thing is I'm publishing it on port 80. We'll talk about why I can do that in just a little bit. Okay, and there you go. And if I go open, should automatically bring over, and there you go. Okay? Yeah. So, oops, that's not what I wanted to do. Let's do that. Okay, so let's go back. And, okay. Yeah, so you can see it's pretty familiar, right, if you've worked with these sort of tools before. Let's move on and talk about the high-level design principles that informed the containerization library, or informed our effort to develop it. I'm going to first show you the traditional approach to running Linux containers on Mac OS. It's a little different than running Linux containers on Linux. And then we'll contrast that with containerization. Now, to start with, we're going to go back to running bare metal, running applications directly on Mac OS. Say these three applications are an Nginx web server, some Flask middleware, and a Postgres database. Now, those of you who are really familiar with Mac OS, I'm talking about unsandboxed Mac OS apps. Mac OS sandboxing gives you isolation, but it's pretty much another talk entirely. We're talking about what sort of isolation exists between regular old Mac OS processes like these, okay? You get virtual addressing, and you have a user kernel split like any modern operating system, and that helps keep you from blowing up your system and blowing up the processes next to you. But amongst everything else you run with your own user ID, it's sort of a free-for-all, okay? I mean, your web server can enumerate every other process on the system. It has access to any file that you own. And if you started it up with, say, like the Mac OS terminal app that ships with Mac OS, it can access everything on your local network, okay? So moving from there, we'll look at just a single container and examine the isolation between the container and the host for now, okay? Now, to run a container on Mac OS, a Linux container, you need a virtual machine, and a virtualization framework that Apple offers is happy to dispense you one. Once you have that Linux virtual machine running, there's a hypervisor that sits in between the VM and Mac OS, and it's there to basically let the app run at full speed, except when privileged operations are involved, and then it acts kind of as a gatekeeper. It keeps things safe with respect to the host, okay? And what your container can potentially access, well, you control that, okay? You control that with your VM config, okay? So like storage, network, CPU, memory, you get to choose all of those things, and those are the only things that your VM sees. So that's how we isolate from the host. Let's now consider containers next to their neighbors and containers and that kernel underneath and basically the system underneath the containers. How do we isolate there? Okay. We use a combination of Linux technologies. I say we, this is any modern container runtime. And they work together to restrict what a container can see and use. There's several of them, and I'm not going to get into all of them. Most notably, though, we're using namespaces to determine what a container has, what it can see, and we use C groups to implement quotas over the resources that it can use, like CPU and memory. And that's how traditional container management works on Mac OS. It runs multiple containers in a single large VM, okay? With this approach, what you have to do is at the start of day, you have to choose the resources. You have to configure that VM and pick the amount of, most importantly, memory that all of your possible containers will possibly use over all time. Now, your containers get to share this common resource pool. And the same thing goes for your host data, okay? So you need to configure the VM to share everything. You pretty much have to share the world from your host into this VM because you don't know what you're going to share with your container. And then when you create a container, at that point, like that mount instruction I had on mine, the volume instruction, that goes from the VM into the container, okay? But you've got all of your data, all your host data shared in that VM. Okay, and that brings us to containerization. Like I said, its design emphasizes security and privacy. And the main thing we do for security that's different from what you saw is that each container runs in its own VM. And that VM, we've really crafted it to have a minimal attack surface. And for privacy, it's basically that you don't need to mount the world into that VM. Every container that you have sees only every VM only gets the data that it absolutely needs and no more, okay? And then remember, we were talking about performance, and you might be thinking, well, starting and stopping VMs, that's sort of an expensive operation, right? And it's something we had to consider. We worked really hard to make the performance more container-like than VM-like. Okay, so let's start with that traditional approach, and this is what we do, okay? We're just VM for every container that we run. Now, each of these VMs is really lightweight. You get sub-second container launch times. You saw it started up pretty quick, okay? The other thing that you saw was that each container gets its own IP address on the virtual bridge. You might have seen that when I listed the containers, like 192, 168, 64.3 or something like that, okay? And that means that you don't have to publish ports. You don't have to use that -- publish that you would use with other things to send things over to your local host. You're not running a proxy or setting up IP tables rules or anything like that. You're getting direct access to it. And that's why you can mount a privileged port like port 80 on the container, because you're not mounting it on your local system. That would be prohibited unless you're running as root. Okay, and then when you're sharing directories and files, you share them only with the container that needs them. Now, since each container is a VM, you have to specify for each container the amount of CPU and memory that you're going to use when you run it, or you let it pick a default, which may or may not suit you, okay? So you have to do that, but the other thing that it means is that when no containers are running, you're not using any CPU or memory. You're not committing all that to some big VM. Okay, so I talked a little bit about, or I referred to a lightweight VM. So what does that containerization library that we have, what does it do to make a VM lightweight? And we'll start by looking at devices. Containerization configures its VMs to use a bare minimum of the devices that the container needs, really only the devices the container needs. In something like this, we don't need a chipset or physical peripherals, okay? We just need a couple para-virtualized devices. One thing we need is a virtual socket, a vSock, and that's going to facilitate communication between the host and the guest. We're going to need a block device to mount the container image into the container. And we would need block devices also if we have named volumes. Aside from that, if we are attaching it to a network, we need network interfaces, a virtual network interface, and similarly, if we've got host shares, there's devices for that, like VirtIOFS shares. And as I mentioned before, containerization, the library is going to allow you to pass down the parameters to configure CPUs and memory. So we've got this lightweight configuration. What do we do with it? What happens when we launch it? Containerization sets up the VM to direct boot the kernel. Okay, what we're doing, we don't need firmware, we don't need a bootloader. And that saves on boot time, and it also reduces the number of moving parts that we have to maintain and keep track of. Okay, the kernel itself has a minimal kernel config. This both shrinks the system footprint. I'm going to stick with that. The footprint and reduces the boot time. So going from reset to user space being ready is really fast. Okay, and then for security, that minimal config also means that you've got a very small attack surface or a smaller attack surface. So let's say we get to user space. Let's look at the initial file system that we're working with. And here I'm not talking about the container image. I'm talking about our image that's running the supervisor, right? That's supervising all this, okay? You know, with a typical VM, it's going to be pretty fully loaded. It's going to have a standard C library. It's going to have dynamic libraries to make sure all the wonderful apps you have run properly. And you're going to have, at the very least of those apps, you're going to have some core utilities like CP, LS, PS, okay? So as with the kernel, containerization, we're trying to strip all that back, minimize, make faster, right? Make the attack surface smaller. Okay, we don't need core utilities to manage a container workload, so those can go overboard, okay? And we'll just say no to dynamic libraries, okay? And even the standalone libc, we really don't need it for what we're doing. So what are we left with? Well, containerization manages everything through a guest agent process, and it's purpose-built for just this one job, okay? The name of that executable is VM-initd. And it's written in Swift, and we cross-compile it on Mac OS over to Linux, and Swift gives us this Linux static muscle SDK for doing this, so we can produce static Linux binary that will then package into an image. Let's look at what VM-initd does before, during, and after we run the container process, the primary workload, I'll say. Okay. The first thing it needs to do is sort the network, okay? It needs to configure the network interfaces. What do you have to do? You have to bring up links, you have to assign IPv4 addresses, and you need to configure routes. And then there are a couple other things you might want to do, like set a host name, configure an etc host file, and probably a resolver conf if you want to resolve names, okay? The other thing we have to do before we start that primary workload is get the container's image mounted, okay? Mount the root file system for the container itself. So we do that, and also we do the same for any named volumes and any host file system shares, okay? Now at this point, we can actually launch that primary workload, and we pretty much go into process supervision mode, okay? So we're just kind of watching things, and the other thing that the user could be doing is running execs, and so VM-initd will launch any exec processes, and then it just tracks everything. When a process exits, it reports it back to the host, okay? And when the primary workload exits, it shuts down the container. Now, the client of VM-initd running on your host gets to orchestrate all this, and so VM-initd presents a gRPC API for doing that. And the final note, it's not in the slides, but all of this stuff that VM-initd is doing, it's doing it like it would with a traditional container runtime. So it's using namespaces, it's using C groups, it's using pivot root, it's using all those things. And that's containerization in a nutshell. So we'll wrap up this section with a review of those three focus areas of security, privacy, and performance. Okay, so our minimal kernel gives us security and boot performance. Okay, direct booting that kernel helps with speed up, gets it up and running quicker. VM-initd minimizes the runtime attack surface, and it also is really lightweight, so it can get that workload up and running really quickly. And then the main thing of running these in individual VMs helps across the board. You get stronger isolation, stricter access to host data, and more efficient resource utilization. Okay, so let's move to the code. I'd like to walk you through some ways to play around with container and the containerization code. The first thing I'll do is describe how you can easily extend the container tool by adding subcommands. We give you a simple plugin mechanism. It's pretty rudimentary, and it allows you to add these features, add subcommands without modifying or building container. And that's the CLI plugins that you see there. And then there's a second type of plugin that we call daemon plugins, and that allows you to run background services. They could be XPC, you could provide network access, network API, whatever. But you can use those to work with the other services that we run to add functionality. Okay? We use the service plugins in container for almost all of our key system components. The one that you would see that isn't that way is the main API server. We're not doing it as a plugin yet. And creating a plugin, well, it's mainly a packaging exercise. I mean, the programming of it is just create a binary, right? I mean, you don't even need to use Swift. You just need to do something that handles commands in a conventional way. Okay, so for us, I'm talking about a CLI plugin. So for that CLI plugin, you need that, and you just need a little bit of metadata JSON, okay? And those two files, you would install them in a conventional location relative to the install root of container, and then when you start container, it's gonna pick it up, or when you run the container command, it's gonna pick up the CLI plugins. Okay, so let's move on and look at a Mac OS application that embeds containers directly inside of it instead of going through the container tool. So the containerization library, it implements all of the core logic you need to work with containers and container images. Some of the libraries you see here, they include OS abstractions and IO abstractions. Being able to work with Netlink to configure network interfaces. And we even have some code for creating ext4 file systems on Mac OS. And we use that to snapshot our images effectively. Okay, and as you might expect, there's a sort of layering that happens here of those APIs. At the bottom, we've got our kind of our low-level system programming stuff and like our primitives for OCI image manipulation. Above that, we've got our core types for virtual machine, process control, IO relay. And then on top of that are our really high-level abstractions for container and image management. Okay. And remember how I mentioned that on that last VM initd slide that we use all the same Linux containerization techniques like namespaces and C groups and whatnot. You can see that at work in that Linux pod construct that we have at the top. Basically, we're using that, we can use that, or you can use that, to create containers that share resources, like a kubepod. Okay, so I've got one more demo, and this one we can just walk through. There's a container example in the containerization repo that you can look at. And I was just gonna stroll through that here. So let me get to that. I hope this doesn't wrap too much. Let's see. Well, I can project this. There we go. So I'm just going to go down. So if you can see, I'm in the containerization repo. So I'm going to go down to examples. And then there's like a CTR example here. There's a README file and all that, and some basic instructions. The one thing I've done already is run a make target to pull a kernel down here. And we should see that there's, yeah, you see there's a VM Linux here, right? So let me see if I can just search and get that. Oops, okay. So we'll go into sources, and there's just one file. So we're talking tens of lines of code here. Our fancy header. Okay, we do a few imports. We start by setting up our terminal, like the terminal that we're running in. We want to put it in raw mode. I should probably tell you why, is that we're just going to run a shell in Alpine for this. It's a very basic example. So we're going to put our terminal in raw mode so we can attach that shell and it won't behave like a child. After that, we need to pick an init file system. So we do publish on GHCR these init file systems. That has the VM initd in it, and it has one other thing in it called VM exec, and it kind of works like crun. So VM initd actually delegates the starting of your containers to VM exec. Okay? And VM init is this OCI image that has just this. Okay? And we're going to pick our kernel, which you saw. At this point, we're going to start that super high level at top of the stack container manager instance. And we're just giving it the things that we talked about, and we're telling it to create a simple network. And then it's just some other administrative stuff. We're going to set a container ID. We have to pick our Alpine image. And we tell the manager to create using the container ID and some basic stuff. And then we get a config back in this block, and we do the rest of our config. As you can see, CPUs, memory, we're passing it in the terminal to attach to, and we're telling it what to run. We're going to run bin sh in root. We'll clean up at the end. And then this bit, the container create is what bootstraps the VM. So at this point, we'll have the VM running, and then we do the await container start, and that's going to fire up our workload, okay? And we resize our terminal and just wait for the container to finish. And at the end, we'll stop the container, and the defer will hit us there, okay? I can show you, I mean, yeah. Let's do bat makefile, just so you can see. There's not too much in the makefile, but the build target, you can see we're just doing a Swift build. We're doing a code sign with some basic, it's basically we need to attach a security entitlement for virtualization. It's one that anybody can put on, and that allows us to create VMs. And then we're just copying the binary up. And that's it. So we'll give it a shot. Hopefully it won't take too long to build. What's that? Actually, I hope I finish early. I'm not gonna do any on mic questions, but I'm happy to talk to y'all and get you set up or whatever. I'm sorry, I can't hear you. Oh, there you go. Thanks. No, we got, yeah, so here we are. We got our Alpine shell. Okay, so. There we go. Oops. Let's try that again. All right. A word on Swift, okay? Let's see. Oh, there we go. Let's do. Oh, I know what I needed to do. So I did it so that my presenter notes weren't showing. There we go. Okay. A word about Swift. I mentioned a couple times how we wrote it all in Swift. So I'd like to share now about why, I mean, aside from Apple being Apple, that we did Swift. And what our experience with the language was like. Your typical languages for this sort of work would be Go or Rust, C, C++. Those would be the usual suspects. And our team has a lot of prior container runtime expertise, but we didn't have a ton of Swift expertise going into all of our runtime work at Apple. One of the things that we liked about Swift is it's got a really good interoperability with C. Swift gives you a really low effort bridging to system calls and C libraries. And an example of this that I dealt with recently was we needed to integrate Z standard decompression into, if you're familiar with that, into the project. We needed to do it pretty quick. And if you look at the Z standard project, it's C, maybe a little bit of C++. But the other thing, if you poke into it a little more, is there's a package Swift file in the top of it. You go into like lib or whatever, there's a module map. And that's all we really needed to be able to import Z standard into containerization as like a Swift library. Is that easy? And really adding support, we needed it for Z standard kernel images because the Kata project moved over to those, but also it gives us Z standard image content layer support too. We did it practically overnight. So like the C interoperability, it's good. Other things, Swift has enums with associated data, so if you need a tagged union, it's pretty easy. And the optional syntax is really pretty ergonomic. It's a safe language. All the major language features are memory safe. And Swift 6 has this structured concurrency and strict concurrency checking that gives you compile time validation against data races. Talked about the static Linux SDK before. This was essential for us because we needed to build that statically linked VM initd and VM exec. And we needed to use library code that we were sharing for both Mac OS and Linux. And finally, being able to directly access all the Mac OS frameworks and features, it just really simplified the implementation of the whole thing, of both containerization and container. So I'll close with a little bit about our open source community, what we're trying to foster, and in broad terms, where we think the project is going. I mean, where we all think the project is going, the community. Now, since we launched the projects last June, we've been really excited by the positive response, and a top priority for us is to encourage contributions and grow that community. We welcome all feedback, whether it's issues or pull requests. We have discussion forums for questions or ideas. A couple recommendations if you want to get started, and these are, I mean, they're pretty much common sense for any open source project, right, is, you know, search the issues and PRs before you start coding, and if an issue doesn't exist, you know, please file one, get some feedback up front on things that you do too, before you just like push 20 files up, right? If it's really trivial, then, you know, maybe an issue isn't needed. We use AI a lot now, and we love it, it's great, but if you use it, please review what your AI wrote before sending that PR up, because then you're just making other people review what your AI wrote, and that's not always fun. And then if you got any issues, just as like any big software thing, clear reproduction steps, try and make a minimal reproducer, and show all your commands, output, environment details, and that'll help everybody in the community triage and figure out your issue quicker, and you can get a quicker remediation for it. Okay. Some other things that we're shooting for. We're looking forward to seeing new projects built on top of containerization. One of the things that's personally interesting to me is using containers as jails for AI agents, right? As basically a way to control their access. And this ability to configure precisely what a VM gets, right? So that even if it escaped the container, it's not escaping the VM, right? And the ability to create multiple virtual networks, and some of them can have internet access and some can't, it gives you a lot of possibilities to let your agent just go YOLO, right? But only within its secure world. For the container tool itself, we want to foster the development of upstream and third-party plugins, external plugins. Looking further forward, there are some features and integrations which we're looking at. Right now, like in the next couple of months, we're really trying to get the APIs stable. Like right now, if you've coded at all against it, we're just blowing things up all the time, and we need to stop doing that. And we need to reduce a little accumulated tech debt. But moving on from that, that stuff will make it easier for ourselves and for outside contributions and third-party projects. One thing we're looking at as far as command plugins is what we are calling a distro plugin. And the idea is that gives you long-running Linux environments with tight host integration. I mean, it's nothing new, right? I mean, it's a lot like what Windows subsystem for Linux would do on Windows. And we have a discussion page for that too. So if you're interested in contributing or you know, telling us how you think it should be designed, go participate on that. That'd be great. We're also looking at getting Kubernetes development environments going for cloud-native development. And this isn't like full-stack Kubernetes integration. We're talking about mapping Kate's nodes onto containers. If you've ever played around with Kind, for example, Kind is Kubernetes in Docker, right? And we've used Kind with a container tool on our own fork, right? But there's challenges with upstream integration. Kind is really built for something else, not really for everybody to map onto their container things. They call it a Kind experimental provider for that reason. So we've talked to them, and one of the things that we kind of both came to see is that, you know, Kind has to do a lot of things because they're not running in containers like we are, like in separate VMs. So, you know, kind of what we all came away with is maybe it'd just be easier to do our own solution for that. So right now we're looking at what a great UX would be for that. And again, we'd love input from anybody that's interested, that likes to toy around with that stuff. We're always looking to improve performance. And one of the areas that we got started on was to make the builder better. Right now, the builder we have a Swift wrapper around Moby build kit running in a container. And that's so that we bridge our Swift APIs to build kit in that container, to the Golang APIs, which all works. It works pretty well. And Moby build kit is great. I mean, it's the de facto solution. But that bridging has an I/O performance cost to it. And so one area we'd like to do is come up with something where we're doing more stuff natively, and that should help build performance. But that sort of thing is a large and complicated task. So just expect more discussion in the community over that in the next year. And then a lot of container ecosystem integrations we're looking at. One of the big ones is Compose. A lot of people want Compose, and Compose is great. We're also looking at plugging in at the Kubernetes CRI level. And dev containers are another big important thing that, I mean, personally, I love dev containers. I want dev containers. So the trick is this. Kubernetes has a nice standard API, CRI, that we can integrate. It's built for integration. Like, it's built for everybody to integrate against. Whereas you're working with a de facto standard for things like dev containers and Compose. And so it gets trickier because there's just such a big surface area there. So we want to do it, and there are community solutions actually for Compose today that you can check out. We've had some really intrepid developers work hard at it, and so I'd recommend trying those out. But at the same time, we're looking at how in the container project itself we can actually move towards getting those things working. And that's it. So to finish up, if you're on a Mac, go ahead, try out the tool. You know, you have the link in the package now, and we love back. Take a look at the APIs if you want to code, and yeah, build your own apps and container features. And yeah, thanks everyone for coming. Yeah, I will be here. I'll do your questions, but down there, off mic. And yeah, enjoy the rest of the show. Thanks.
Thank you, John.
you can do a little sound test, it should be
Sure.
that button. Some of them are, some of them have a little weird, swivel, and then this one I think is just the button on and off. But we can do a quick sound test.
Yeah, sure. My voice is really terrible because of the long flight I had, but I think that's not going to be a problem.
Okay, no worries. Yeah, it sounds fine to me for now. And I think once you're on the mic, it should
Yeah.
be good to go.
Yes. Okay, 1, 2.
Yep.
Perfect.
Sounds good.
Yeah, I'm going to switch it off.
afternoon, everybody, and welcome to everybody that might be joining us again for Cloud Native Days or here for the first time. We've got another great talk coming up on green observability, what needs to shuffle in open source. So everybody please give a round of applause to Diana Todea.
Yeah, thank you so much, and I really appreciate it. This is my first time with SCaLE and my first time in California, and as you can hear, my voice is really husky, which gives it like a cool, groove, but, I didn't aim it like that on purpose. It's just a long flight. I'm coming from Spain today, yeah, let's kick it off. So what I'm not doing when I'm not working as a DevRel at Victoria Metrics, I'm an Open Telemetry member and contributor. I'm a co-organizer of Cloud Native Days Romania. So if you're ever found in Europe, in Romania, you can give it a go. And I'm a co-lead of CNCF Neurodiversity Group. This is part of Merge Forward initiative. And I'll have a call-out slide at the end and talk a bit about that as well. So before I get into like the whole talk, I want to maybe also give a bit of a background, a bit about myself and also the talk. So I've been working in tech for 16 years and in observability for the last 7 years. I was, before joining the, let's say, a more official community role, I was an SRE and a DevOps engineer in observability. So yeah, I kind of like handle a lot of situations, which brings me to this talk today. The slides, obviously, you can download them from my GitHub repo, and they're also uploaded to this to the repo from SCaLE. And about this talk, I presented like a smaller version, like a shorter version of this talk at FOSDEM conference in Belgium this year. I don't know if you know about FOSDEM. Anyways, this open source conference in Belgium that is really popular because it has like a lot of dev rooms and a lot of talks that they come from different areas of open source. So this makes it really interesting. And this talk, I had only 50 minutes actually to present it this year, was part of the energy dev room. And it was really interesting because it made me also research a bit more besides the observability and software ecosystem, and also was a very good opportunity for me to learn more about the carbon footprint, energy consumption, etc. So for me, I've been working in observability, like I said, for a few years, a long time, let's say 7 years. And we all know that the cost of observability is pretty high. Obviously, it really depends on the company you are parts of, but generally speaking, if you're not careful with how you are driving your observability costs, they tend to get away, right? And it's not a small issue, it's not a superficial issue. Actually, an observability bill can be around 15–25% of an infra bill. Also, if you're adding AI, LLMs to it, right now everything is just exploding. So we need to be careful around not only the costs, but also the resource consumption. And that bears in mind the question why sustainability matters in observability, and why we should be, let's say, consider it like a very important topic to bear in mind. Well, obviously, besides the costs, we also bear the cost of more telemetry, the resource consumption, the energy that is being spent on all this telemetry, and the carbon footprint. And while we are all thriving to take care of our planet, I think it's also important to think outside of the, let's say, software ecosystem, and in particular to observability as well. So I'm going to walk you a bit in this area of where it all started, like where the green software, let's say, definition or concepts began, and how slowly it evolved into the nowadays speech about green observability. So I'm not sure how many of you are familiar or more familiar or not with the Green Software Foundation. No, perfect, awesome. So that was for me actually a novelty as well last year. I didn't know about this foundation. Last year I participated to a conference, a platform engineering conference actually, And he was a person that was part of the Software Foundation at that conference that gave a really nice talk, 1-hour talk about the mission, the principles, and everything that they want to do. So basically, the Green Software Foundation was founded in 2021 by various companies and with the support of Linux Foundation. And its mission is exactly to reduce the carbon footprint in software. And from all this statement or from this mission, they also started to begin to focus on very particular actions to drive the reduction of carbon emissions of software. So, for example, 3 main important actions of this foundation is to use less physical resources, less energy, and use that energy more intelligently, right? So they're really thriving for it. It's an open source, obviously, foundation that is really nice. It drives, like, for example, more companies to join and help them in this mission. And they're also, right now with AI, they're also focusing on, how we can drive AI, let's say, initiatives to be more, and, to be focused more on sustainability. While also researching the idea of green observability, I came across a few protocols, or let's say a few standards, because I wanted to understand, what's the link between the green software and actual observability. And I wanted to know if the Green Software Foundation actually made a very particular accent or added a very particular focus on observability. So far, it hasn't. So that's, something great because we can focus on something new right now. And also, I have some protocols about the greenhouse gas protocol. So that's the first one, which is a globally recognized foundational framework for measuring and reporting emissions. Then the other 2 ISOs, so the first one is an international standard that provides principles and requirements for the quantification and reporting of greenhouse gas emissions at an organizational level. I know it's super long. And the last one is actually focusing on carbon footprint of products across their life cycle. And this one, actually the last one, can be applied to specific software product or service. So yeah, you might ask, why is this important? So it's important because it drives, it gives us a bit more context, educates us a bit more, like how things started and what we have currently at the moment in the industry and in the market. And actually, something really interesting, the Green Software Foundation came up with this standard. Well, it's not yet a standard, it's more like a specification, which is called the Software Carbon Intensity Specification. And what it measures how much carbon and our software emits per unit of work. Well, I'm not going to explain like the entire equation there if you want. I mean, I can explain it, but what it is basically focused on the idea of energy consumed by software. And it's not a total, it's a rate, right? So it makes it comparable, it makes it trendable and observable. So when I stumbled upon this specification, I was like wondering, okay, but can we apply the SCI actually to observability? Would that be a very interesting use case for it, and how we can apply it? So that's food for thought. I will be very interested to actually continue this, let's say not only a theoretical realm, but also in a practical way. I would even go a bit further than that to explain, to want to actually add this specification as a SLI, as a service level indicator for observability. And that would be something cool to have in the future. So in economy, for example, we have something called sustainability paradox. And is actually when you have when trying to improve the sustainability, and efficiency, and actually when we have systems that have lower costs, we tend actually to buy more and consume more. And that makes actually, it's driving more the environmental impacts and instead of reducing it, which makes it a paradox. And actually, yes, it has a name. It's called the Jevons paradox or the rebound effect. And it also obviously hits the software industry. And if we drive a parallel with observability, we can talk about the same, about an observability sustainability paradox. Why? Because in our rush, or let's say in our ambition to have more observability data, to produce more observability, and to have more insights basically into our systems, we are logging too much observability data, and we are raising actually the system overall carbon footprint, which is not something like we want to achieve, and definitely this bears in mind the question, how well are we designing our observability systems, right? With the idea of sustainability in our heads. So for that, I wanted to extrapolate a bit and take the example of a few open source CNCF projects that will lead us to the idea how much basically we are not focused on sustainability or green observability at all. And for example, if we would just take a random example from Prometheus, it comes with default scrape configurations that collect everything. Also, the scrape intervals, they're not very adjusted in the sense that the default ones, they might not reflect the reality, or we might not even need to, have such high, let's say, scrape jobs intervals. We also don't need to have high cardinality labels like pod request ID, user ID, session ID, and we necessarily don't need to have the same retention for all metrics. So what we want to do instead, we want to collect less. So it's not necessarily a game for ambition of collecting everything. It's actually a game to be a bit more stingy and actually collect for the basics. And yeah, it's true right now because we are a bit spoiled that we have a lot of very cool tools, projects, we can do everything right now. But unfortunately, we are not very analytical, right? We are not thinking a lot that with few metrics, actually, we can have more than enough information that could give us insights into our systems. So for example, I was talking about collecting less, right? So we could keep only the metrics that we actually need or actually use, we actually use. That in effect, if you look at reality, we only use 50% of the actual metrics that we are designing for. Then we can actually drop the high cardinality labels early. And as an effect, we can reduce the time series count, the memory usage, and the query CPU. So, right, if you're going to think, why is this green observability? Why these actions represent sustainability? Well, yeah, because in the effect, we're going to have fewer time series that will produce less RAM. Then we have smaller time series database with less disk input outputs, faster queries, less compute time, and obviously just maintain the same SLO visibility, but will have lower footprint. The same thing for Loki. So if we take a couple of, say, logging open source projects, basically the defaults are not necessarily the best ones for green observability. Why? Because we are logging everything at the level of info. Then we have these like very large unstructured messages. Usually we have long default retentions. And yeah, logs are actually the largest storage consumer. We might double think exactly how we want to keep those logs. So what we want to do instead, maybe we want to drop the debug logs before indexing, keep only actionable log levels, reduce ingestion and index size. And yeah, the same it goes for green observability, because less log volume obviously will occupy less disk, smaller index will drive the faster queries, lower ingestion rates, we will have less CPU, and obviously we'll still be able to find errors quite fast. So for Fluentbit, normally in Fluentbit the same as default. We have logs that are being shipped raw that include noisy or low-value logs. Then the filtering happens too late, and we have wasteful network or storage usage. So there are a bunch of things that happen, with the default parameters that we want to double think about that. So in this case, we want to filter, drop, normalize logs before shipping, drop health check noise, control label cardinality early, and reduce the network traffic. So it will be great because from a sustainability point of view, we'll have early filtering that will have the best impacts, smaller payloads with less energy per request, and cleaner logs with better signal-to-noise ratio. If we think about telemetry, so let's say I took more like in terms of metrics, logs, and traces. If we think about open telemetry, yeah, people nowadays, it's very hard to capture the right telemetry data that we want. Normally, yes, we do collect lots of telemetry data. So if you are like sticking with the defaults, or we're not, designing very well the telemetry around it, we're gonna sample 100%. And then every request will create a span. The CPU will be used for the span processing. Then we have memory overhead, storage explosion, more storage, and the traces basically will never be viewed or analyzed. So maybe we want to do something else. So for example, we can also use head-based sampling in the hotel collector configuration. That will give us, more, let's say, green methods. We'll have a more green approach to telemetry. We'll have like 90%, let's say, reduction in trace volume, lower back-end storage, processing costs. We can have the same visibility, but we'll still see the latency distribution and errors. We can also think about another solution that will be the same in the hotel collector configuration, to use tail-based sampling. And in that case, we can keep the errors, high latency traces, and rare endpoints. So in this particular case, we'll actually be able to use only 5 to 20% of normal traffic and store 100% of the actual important traces. There's also a third solution with this. So if the traffic spikes, we can reduce the sampling percentage automatically, maintain constant resource envelope, and when the system load increases, we can reduce the telemetry loads. And yeah, in the end, we can have the green observability that scales responsibly. So anyway, these are a few examples that I wanted to give, because definitely in open source and beyond open source, in observability, we are not, let's say, designing for sustainability, right? So we're not having this as in mind. As the first thing we know when we wake up, we're not thinking about sustainability for sure. So the idea would be like, okay, but what if we build green first observability? So what if we actually, in the design principles, in the actual planning, we come with this, objective, and we want to focus on sustainability. So we can actually think about building I think it kind of, does it drop on and off? Yeah, right, okay. Default short attention policies, right, so we can have, for example, cardinality warnings with energy impact hints. Anyway, this will be like, ideal world, nice to have. Probably some of them, they exist at the moment, so anyway, that's nice to know. sampling presets based on energy budgets, storage footprint, trend alerts, obviously not collects everything and collects intentionally. So there is a cool project that I'm pretty sure you heard about it, Kepler, it's a CNCF project that uses eBPF and system counters to estimate energy use of container pods, virtual machines, processes in Kubernetes environments. It's really cool because sometimes, I was talking at some point with a Kepler maintainer or contributor, and it's really cool that what they're trying to achieve, and the use cases around Kepler. So most definitely, it's exposing the energy consumption via Prometheus, right? It can also be integrated with observability stacks that include OpenTelemetry. However, if we are backtracking to this SCI, so the software carbon intensity specification, is not natively implemented with it. It would be nice to think a bit proactively, or think, how we can actually make this kind of projects work together, or at least make them integrate natively with one another. And that's something that I will also want to explore in the future and keep coming back if I will ever give this talk again. So one last, let's say, use case that I want to focus on is parts of the Victoria Metrics open source projects. Because at the moment, the way we are focusing not only on the observability pipelines, but also internally in the, let's say, in the coding practices, etc., of our development teams, is something that maybe we can share with the community, and we can explain, for example, what worked for us. So it's our own use case. So it's nice to share with the community. So I will start with the language choice, because it's something that always comes up in discussions. So as programming language, for example, you use Go. Many companies, or anyway, many companies usually prefer Python, but we kind of focused on Go because it's very simple, it's more efficient, it's quite sustainable to manage. And we do make some parts of Python codes, like the majority of all code is written in Go. So that's pretty cool. Also, another point I wanted to make is about the careful use of external libraries, because I don't know, but external libraries, they often come with a lot of features that we don't use, we don't necessarily need, and they just basically add more carbon footprint there, they waste resources. So yeah, if you're a software engineer, developer, you need to be careful when you want to use these external libraries. Then actually, obviously, you can practice the green coding. That's, I heard about, obviously, other companies, they do it. It's really nice because basically what happens here is that engineers come and they refactor and keep refactoring codes. For example, they drop like unnecessary code. They try to come up with different algorithms to improve the code and make it work fast. So yeah, that's nice when you see that the actual engineers come and stay and think a bit longer before they ship, I don't know, 1,000 PRs that probably don't solve anything. So it's definitely, how can I say, an intentional, this is what I mean, an intentional action that's definitely interesting to have. The part with observability and profiling, and I noticed that other observability vendors are doing it, and this is actually pretty cool. When the engineers actually when they actually use their own internal tools, observability tools, to understand what they're producing with their codes. Basically, with profiling, you can understand, if your code is actually useful or not. You can do synthetic monitoring, etc. And that's always good to use observability, not only for the external world, but also for your internal projects. Right, so going a bit even further into the use cases here, all these, let's say, like different actions that I was explaining were actually successful in reducing the energy costs in, for once, Victoria Metrics. So that's a metrics open source project, with achieving like less infrastructure costs, the costs for the network were reduced, and also the energy costs. So the benchmarks, obviously, they're published, they're online, they're free to use, and for us, it were an energy reduction. And I wanted to present you a short demo here, the Cardinality Explorer. That's one of the unique features in Victoria Metrics. And you can obviously scan the QR code to go directly to the playgrounds. And here, so this is the playgrounds. I'm not sure if it's super clear in the back or not. So going to the Explore Cardinality here, we have something called metrics names with the highest number of series. And we could actually see when they were last requested. So for example, if you see there's 0 and you have a metric that's expensive and it kind of like, explodes your time series database, then maybe you want to delete that from your code and relabel it. And also you can check the different labels that drive that cardinality up. In the top queries, we also have queries most summary time to execute and different other for heavy queries. Or queries that take more frequent time to execute and more memory to execute. That's pretty cool because as an SRE, I always like to look at how observability vendors and beyond, they design their own dashboards. Not only thinking about what cool visualizations you can have, but also thinking how you can actually debug an incident and start thinking about the queries that drive the pain or might be the cause of an incident in production. So for the logs, basically it's the same principle. And here, well, this will take you to the documentation, but what I wanted to show you are a couple of features here that hint to how logs in Victoria Logs are actually running faster. There are actually two things here. I mean, just one, and the other one is just an explanation that takes you to the playground, the QR code. So this is streams, right? So it's log streams that basically what they do, they group stable identifiers like namespace, pod, service. So all the log are basically grouped together for that specific instance. So it makes it actually faster to take that, to group that stream fields and give you the results. And it's interesting because, so for example, the message, I don't know, let's say, for example, Kubernetes pod IP, and they're separate because they will always change. So they're not parts of the stream field there. Also in the overview, so once you check the playground, in the overview section there, you have a couple of different tabs that can link you to the cardinality of the stream log. And it's interesting from, let's say, an engineering perspective, how you can debug this and understand a bit more, okay, how is my log doing, or if I can understand how it's driving the cardinality up, etc. So for Victoria Traces, which is currently not in production, but is still available, and you could test it if you want to, we are adding the same features for sustainability. And yeah, it's good that, at least from our perspective, we are trying to drive this from the beginning, right? So we are trying to design these projects, we are trying to design products with very specific focus on sustainability. Right, so this part is, I wanted to make an extrapolation with a few, so I'm not, no, but anyway, it's, in economy, there are a few principles that are called the 9 R's, which were reduced to 6, that are refuse, reduce, repair, resize, reschedule, and repeat. And what I did like, for example, talking to the community around sustainability was the fact that also these kind of 6 R's, we want to apply them in Kubernetes. And I really liked the community that were explaining this, how they can be applied to Kubernetes, and I like the idea, and I actually put it in usage for observability. So if we take it from these 6 R's and actually apply them to observability, what we can have. So we can definitely refuse and reduce the useless metrics, so we can collect a lot less, obviously, and also the logs and high cardinality labels. Then we can repair definitely the noisy alerts, broken or inefficient queries. We can resize with rollups, downsampling, and stream aggregation. For rescheduling, we can change when, how we observe. We can lower the scrape frequency. We can use adaptive sampling, on-demand deep diagnostics. And for repetition, obviously, we can use the same proven signals, queries, dashboards, alert patterns across services and teams, and yeah, stop wasting time reinventing everything. So I'm almost at the end of the talk. So for me, the takeaways, and obviously I think it's a very important topic, green observability and in general sustainability. It's nice to have, and definitely we should start applying the Green Software Foundation actions from day one. Would be, let's say a safer world from that perspective. Also, green observability, it doesn't depend on specific tools. It's not, suddenly become greener if we use, I don't know, Prometheus or log or telemetry. Or it's all about intentional design choices. And we are all responsible to maintain it, right? So it's not necessarily that we need to wait for a manager or company to say, oh, we are becoming green right now, but it's also individual decision, right? So in the end, as engineers, we all decide how we're going to refactor our codes and how we like to work on a daily basis. And this one is the part that I was mentioning at the beginning with the Merge Forwards initiative. That's a new initiative from CNCF, which is really cool because I'm also part of one of these groups. I'm a neurodivergent person. So right now in the Merge Forward initiative, we have 7 different groups. You can check the QR page, it will take you to the explanation. We're gonna be at KubeCon Amsterdam and always at future KubeCons also here in America and hopefully at other KubeCons across the world. Yeah, so it's really nice that we are finally giving a voice to underrepresented groups in tech in open source and CNCF. We had very nice, let's say, collaboration last months, exchanging ideas, meeting for the very first time, like face-to-face, discussing a lot more, and starting to grow as a community. So if you have obviously, and if you want to join, don't necessarily have to identify with any of the underrepresented groups. You just, you want to join or be an ally, please do so. We are always looking for more friends to chat with. I left a couple of resources, so everything I was talking about right now, you can definitely check it out. There's more about this on the CNCF Slack, more about this on the community. This was obviously just a how can I say, a taste, right? So definitely there's a lot more going on and there's a lot more to do. Hopefully this talk can resonate in the future and we can do something more about it little by little. Also, if you want to chat with me or ask me any questions about Merge Forward, CNCF, whatever you want, you can chat with me. And that's about it. Thank you so much for indulging me.
So we do have some time for questions. Are there any questions from the audience?
Hi, I really like the idea of being able to log just based on an event, right? Do you know if anybody's kind of built any proof of concept on that as of yet, or is that something that's still kind of new
So do you mean the part where I was showing the stream here?
So you mentioned where, you know, if there's certain events, maybe increasing the logging fidelity and kind of dynamically increasing or decreasing the logging based on that event. And I'm wondering if there's anything that you know of right now that works like that.
Okay. Okay. So you want I wanted to understand, like, if you're referring to this part because, yeah. Sorry. Ah. Okay. Right. Yeah. Right. So if I know, yeah, the question was if I know any tools or any projects that are at the moment. Sorry. If you can repeat again, my voice is like. Yeah. Sorry. Give me 2 seconds.
No problem.
Right, so there are any tools like or projects that at the moment they can dynamically, group logs based on
Or adjust volume, right? Like
or
I think that
volume.
was I think that was one of the things you mentioned was is changing the volume of the logging
Right.
based on an event or some kind of signal, right?
Right. I'm not sure. I mean, there are something around that idea, so that's why I was mentioning it. So parts of me mentioning a few open source projects was to actually focus, like, obviously on theory, but beyond that, with Victoria logs that I was showing is like maybe focusing on the cardinality in logs, and like, grouping, how can I say, specific identifiers in a stream log that will make it easier to, query, will make it faster, but not necessarily about the log, the volume of the log, right? Dynamically using that. I mean, in theory, somebody that probably designs that could give you a more, I don't know, like a more direct response. But at the moment, I don't have any particular use case in mind, or I don't know myself of any use case in that case. But it's a very good question. So I will also be interested, and I'm going to do some research about that too. Thank you.
Thank you.
Yep.
So I thought it was interesting, the idea that the things that are good for sustainability are also good for budgets, right? And so the things that are also good for budgets also sometimes can be good for compute costs, and just, good practices also can result in good sustainability. So I thought that was just an interesting analogy. But I had not heard of Victoria Metrics, so I'll definitely check you guys out. But as a Grafana user, for example, and a Prometheus user, a Loki user, what are some good ways to identify what really is important and what is not? Because I definitely know that we're tracking a lot of metrics that we don't use,
Yep.
and I can associate logs, I can associate dashboards back to which metrics are there. But I know that there's a lot of people who are just hitting the explore button and looking at things. So is there any good tricks or techniques to identify what's important, what's not? Especially if you're if you're doing Kubernetes, like everybody should pay attention to X. All these other things are rarely used, right? So any rules in those regards?
Yeah, definitely. Thank you for the question. Yeah, those are very good questions. So basically the idea, there's a very, how can you focus actually on the best practices in logging, metrics, whatever traces, what actually is important to log. Because obviously all of us have a curious mind, and we necessarily, definitely go a bit crazy there and start, looking at a lot of metrics. So basically, that's, I think, especially in open source and especially in CNCF Cloud Native, that's why we have the projects and we have the maintainers and we have the best practices. For example, in Kubernetes, we have actually instrumentation, a special interest group that focuses on the best practices, like specific, how can I say, specific levels of metrics, log.
So you're saying that there's already some published
Yep.
best practices for what to focus on there at that level?
Correct, and it depends, obviously, it depends on the project, so not all of them have them, exactly. For example, with OpenTelemetry, because it's let's say the new kid on the block, it would be nice to, but this is like actually an ongoing effort at the moment from the community part, that they are focusing right now on instrumentation, right? So they keep communicating with one another, for example, OpenTelemetry with Prometheus, try to figure out, okay, what are the best practices where we can reach each other based on the level of experience of other graduated projects. So, for example, Kubernetes has that. So it's called instrumentation, special interest group, and it works at the login and the metrics level. You can give it a go. Also, it's a repo called Mixin that is based on alerts. So definitely there's a lot of best practices around that. Yes, it needs more love, and actually I gave a different talk about that, focused on instrumentation in Kubernetes. It needs more love around the onboarding for beginners, for developers, because there's a lot of ask, just like you ask right now, like, I don't know, I'm a developer, I'm somebody new, just the things that will really pop on that page. So this is something that we brought up to the community quite recently, and right now we are building a whole case around it, because if you go to the Kubernetes instrumentation page, you have a huge list of, of things, and you're like, okay, but what should I do? Which one should I pick? Which one is the basic? Which one is the advanced? Of this actually open issue last year, so we are working on that. What I would suggest besides that, so besides the official way of looking at things, depending on each project, there's always going to be a best practice. There's always going to be, but that's more like not necessarily documented. It's more like an experience, how would I say, companies or engineers that are more experienced that know exactly what to log in. If you search like online, for example, in Prometheus world, there's a repo that will give you a bunch of alerts that you can definitely implement. It goes a bit more than the basic level. It goes to intermediate, a bit more advanced, but you have like the whole world of alerts there around Prometheus. And I think it's a very, very good repo, definitely worth checking out. But around the best practices is something always that the community should definitely strive to better enunciate. So what I would suggest, in effect, and it's something when I used to work as an SRE, is always focus on the very basic of those alerts or very basic of those dashboards. Never do something that is not needed, so always think twice and basically be very, very stingy at that level. Why? Because you're going to complicate your life, you're going to complicate basically your infra, you're going to spend time actually maintaining those alerts over and over again and going beyond alerts, dashboards, and you know that's the very first level that you're going to have when you are dealing with infra. And obviously, as an effect, you're going to drive your observability costs, your budget, you're going to eat all that budget just on a few alerts and dashboards. So I totally get it.
Okay. Any other questions?
Thank you for the talk. About logging, some people were shocked to discover that pod logs get written to files in var log pods initially, and then from there they get tailed by something like FluentBit and then shifted to the logging stack. Is that generally true? And if so, is that something worth optimizing for like less disk I/O?
Okay, can you repeat it again, but like a bit further from the microphone? Sorry, I'm also a bit deaf because of my...
So is it generally true that
Yep.
pod logs get written to files in var log pods first, and then they get tailed into the logging stack?
Right.
And if that's the case, is that worth optimizing for less disk I/O, for example?
If that's the case, sorry?
Is that something worth optimizing?
Well, yeah, definitely. I'm not sure if it hasn't already been done, yeah. But definitely. I mean, you have a very use case. I mean, I do want to say it in a way like that's a question, but anyway, definitely, obviously, this is always something that we can explore, yeah.
All right. Any final questions?
En español. I'm just kidding.
In Romanian?
Yes.
So, will not. Basically, my curiosity is more for your personal experience. So, we share together a lot of technologies like Prometheus, OpenTelemetry. In this last year, OpenTelemetry has become more standard than what it was. But in your career, 16 years, you mentioned at the beginning, how is your feeling about how we adopt logs? Where are we failing on monitoring? In example, we are getting out from solutions like New Relic, Splunk, also Elasticsearch. We have a lot of experience on failures because we were just ingesting data and not using that data. In your experience, what would be something that you would do if you enter a company that is piling up a lot of data and is not using it like you do in your demos or aggregations, logs, tracing, metrics, the pillars of the observability? How is your suggestion or suggestions for people that are entering the observability world seriously now?
Yeah, perfect. Thank you, Fabrizio. So the question was like, what would be your advice to, let's say, people that start right now with observability and start, looking at the observability signals and what they need to ingest, how to do it, how to design it, etc. Based on our previous experiences with so many logging tools. Yeah, definitely. I mean, right now we have a plethora of tools and projects and whatnot. The same like what he said earlier is like always look at the basic, try to think very, how can I say, must to have type of level, and is also like big. It's very hard, but you have to do it at test trial, right? Because unless you're gonna test that specific technology, then you're not gonna know what it produces or how you can play with it, right? So people will definitely gonna, I don't know, pick, say Elasticsearch or whatever, and give it a spin, right? And see if it does what it should do or not. But the idea is, I think it's more about education here. So how do you educate yourself in designing observability pipelines, and also how do you think about green observability? You don't need so many things to begin with, right? Depending on the infra, the infra that you have in your company, you don't necessarily need all of that, So you can definitely start with very few things, few metrics, logs. Tracing is the most expensive one, but if you really need to have it, then, okay, you can do it. I know other companies that, for example, have entire stacks, observability stacks made of open source, and they keep, like, for example, OpenTelemetry, Zipkin, Jaeger, and God knows what, because not one is sufficient to realize, to complete the entire visibility on it. So it's hard. I think experimenting is the most important tool here. There's definitely not one solution because, I could go the vendor pitch way and say, okay, try Victoria Metrics or whatever. That's not the idea. The idea is that what you want to achieve is something simple or not. If you want to stick with design principles, then stick with those. And that's why I think the whole appeal of green observability is to focus on very simple, very important, how can I say, strategies when you define observability. So I've been part of SRE teams that were saying, okay, we need to redefine our legacy observability, we need to cut, we need to adopt more open source. We came with like POCs over and over again, how to do that with open source, and in the end they refused them all. Why? Because it's way easier to use a commercial vendor than it is to use an open source one. It's very hard to actually design something, customize it yourself, manage it yourself, than it is to just use a plug and play tool from an observability vendor. So yeah, sticking to the basic, to the simplicity, to whole design around green sustainability, it's very but yeah, it takes a village in that case. Yeah.
All right, any more questions? We still have a bit of time. All right, well, great talk, Diana. Thank you very much. Really
you.
great engagement from the audience.
Thank you,
Round
guys.
of applause. And the next talk here in this room is going to be on data in Kubernetes, and that is going to be at 5 p.m. So in another about 25 minutes, we'll have the next talk in this room.
Test, test. Whoop, test.
And then
One, two, one, two. 1, 2. Yes. 1, 2, test. Yes. Thank you. 1, 2. That works. Yes.
Hey everybody, welcome back to the Cloud Native Days track. In our next session, Matthias Krauls is going to explain to us how we should be storing our data on Kubernetes, particularly for the most challenging use case, which is databases. So with that, please, everybody welcome Matthias to the stage.
Thank you, Josh. Welcome. Hello, Cloud Native Days LA. I hope you've been enjoying the conference so far. At least I know I have been. And I'm going to talk here about databases, which is maybe a bit of an odd topic in a Cloud Native room, but I'm going to try to tell you what we do. So my name is Matthias Krauls. I live in Belgium, in Ghent, so I'm a long way from home. And I've been an open source user for a very long time. I started in my teens as a Linux user and then later administrator. Early on in my career, I was a PHP developer on your typical LAMP stack that you know in the early 2000s. And no one in our team back then had any idea what this M in the LAMP stack meant, the MySQL thing. Our sysadmins did apt-get install MySQL server, and that was about it. But there's a lot more to it. So I got involved in learning MySQL, becoming a MySQL DBA, and I'm currently employed at SCaLE, where I take care of our enterprise customers in the post-sales cycle of our process. Typically, I speak to DBAs, so they don't always understand what Kubernetes is. I think cloud native people should understand what Kubernetes is. But I looked up on Wikipedia, and the definition that Wikipedia has, it's an open source framework for managing, deploying, and scaling containerized applications. So it's typically for applications. And a containerized application is something that is typically very lightweight, very portable, and self-contained, which a database typically is not. So running a database in Kubernetes is maybe a bit of a strange thing to do, but I know several people tried and failed. We tried and we are quite successful at doing so. So I want to tell you a bit more how we do things. The title of my presentation was Stateless Storage, which is a contradiction, I think, because storage is typically stateful and not stateless, because you want to keep what you have. So the difference between stateless and stateful is typically on a stateless application, you run your requests independent from each other, and the requests don't know about one another. So if you typically think of your web server, your application server, or a DNS server, you just ask it something, it gives you a response, and it doesn't store anything in the middle. While stateful is typically where you do store things, and typically in a database you want to store the state of the things that you do. So first a little bit about PlanetScale. We were founded in 2018 by the team that was originally developing Vitess. And Vitess is something that grew out of YouTube. It was founded in 2010 at YouTube to solve the problem that they were growing just a tiny little bit, and they had to scale their databases. And they reached a part where they couldn't buy servers big enough anymore to host their databases. And at some point, they developed Vitess to help shard their data on MySQL. And then Google decided in 2018, end of 2017, that they wanted all the large data sets within Google to migrate to Spanner, which was a new product that they were launching in their own cloud. And they were thinking like, we have to eat our own dog food, so we have to have our own data sets go to Spanner. And what they did is they released Vitess as a project because it was still interesting, they thought, in the CNCF Cloud Native Compute Foundation. And then the core developers of Vitess left Google and they founded PlanetScale, initially to sell support for Vitess and to develop it further in the open source community. But in 2021, we kind of decided Vitess is a very complex beast to run, and we know how it works. We're pretty good at running it, so why don't we run it for our customers? And that's what PlanetScale is doing now. Originally, we were only a MySQL Vitess-based solution, but last year we also started doing Postgres, and we run all of our databases on Kubernetes. So I've told about Vitess already, so this is something more about that. And so a big thing about running a database is that you really want to save state. Most people kind of like their database to save the data that they put in there. Not everyone wants to run it on a black hole engine. But databases can become quite large, and that makes them very slow to operate. Slow for any operations like backups, like moving data over. And we typically think about running databases in the cloud as running them on the cloud block storage, like EBS in Amazon, like persistent disk in Google. And that is network attached storage. And that is slow compared to local storage. Because there's a round trip to the storage. And if you have hundreds of thousands of QPS per second, those few milliseconds that you have to transfer back and forth to storage makes a big difference. So at some point, we decided, why don't we run our databases on the local NVMe storage that the cloud providers have, But typically, that storage is called ephemeral storage, because whenever you stop your virtual machine, the storage is gone, and you cannot get it back. It's not really meant to be stateful, so that is why we've been talking about stateless storage, because it's running on an ephemeral disk, but it is really fast. So you can get a lot of good I/O performance out of those disks. But obviously, there are some problems with this approach. Like, you run a database, your client talks to a database. If you would run it like this, I know you can see quite from a distance that this is not a good idea if you run on ephemeral storage with a single server. As soon as your server crashes or you take it away, your data is gone and no way to get it back. So first thing you do is you start adding replicas. So MySQL is particularly good at replication. We learned this year that Postgres can do it too, but there's some caveats there, so we had to patch it just a little bit. But MySQL is really good at replication. So what do? You put replicas in multiple availability zones, and you start running it like this. So you have copies of your data, you have a replica ready to take over if your primary goes away. But still, you're now running at least one, possibly n number of servers that you're not using. The client is only talking to the primary. So you're going to add load balancers. A load balancer to a primary is always having one backend on the backend, yeah, because you only write to one location. Because if you start writing to multiple locations, you start getting split brains, and you replicate that data to your replicas. And for the replicas, you can just load balance your traffic across all the replicas you have for reading, which gives you a good scale out if you have like many people have, a read-heavy application. Like, think of your typical web shop that you would browse. You typically browse different products before you decide to buy one. So most of the workloads on the internet are read-heavy. So really easy to scale out for reads by just adding replicas. Those replicas provide also the necessary copies of the data. So if something would happen to your primary, you can safely flip over to a replica and still have everything you need. It's not completely safe yet by just running with replications, because accidents do happen. DBAs are only human. Developers are only human. So sometimes you do something wrong and you need a backup. So what you do is you start backing up your servers to object storage. That also gives you a persistent copy of your data. So if all hell breaks loose and all of your database servers would go away, you still have your data in the object storage. And the object storage in the cloud, like for AWS, the S3 storage, as well as the Google Cloud Storage in GCP, they both give you several nines of durability. So we are quite certain that if you get a successful backup in the object storage, that you will not lose your data. That graph looks familiar, like the Vitesse architecture. Like what Vitesse does is you have the load balancers here. You have several VT gates which you can load balancer. VT gate is the proxy, and then on the back end you have several MySQL clusters that you can shard into multiple shards to distribute and scale your data. This Vitesse runs MySQL. There's a VT tablet next to each of the MySQL instances, which manages the MySQL protocol, the MySQL daemon. And it also communicates with the topology server, which is up here. Vitesse supports etcd, just like Kubernetes runs etcd. It also supports Zookeeper, and there's still some support for console, but in general, when you would run Vitess, we would recommend you to run with etcd. That's the service we also run at PlanetScale for our topology servers, and it's been proven to be very stable and very good. There's a bunch of side processes to Vitess, like the control daemon to make changes to your cluster, VT orchestrator, VT org, to do high availability if your primary tablet would crash or would go away, then VT org will promote one of the replicas to become the new primary. And then there's a VT admin UI, which gives you a graphical overview of what's running in your cluster. And so Vitess serves millions of QPS in production every day. All of these companies are running Vitess in one form or another. We are PlanetScale. We are on this slide. We run everything that runs in PlanetScale on MySQL runs on Vitess. We don't have any plain MySQL offering. We only have a Vitess offering for MySQL. That's different from our Postgres offering. While MySQL always runs on Vitess, Postgres still runs plain Postgres. We are currently in the process of developing a tool that we've named Niki, and that's going to be the Vitess for Postgres. So we are building that out, and we hope to release that later this year. And we run some of our databases, not all of them. Like for some of our use cases, some of our users, EBS storage or persistent disk storage is still good enough if you don't have a very high QPS or don't have a lot of data. Running on EBS is still good enough. But for the databases that are more demanding, we run PlanetScale Metal. And we run your database on ephemeral storage. So we run on the ephemeral disks, and we make sure that we don't lose your data. This makes your database really fast with virtually unlimited IOPS. Well, there is an IOPS limit to what the NVMe drives can do, but despite our best efforts, we have not been able to find it. So far, we haven't found the limitation. We run our clusters in multi-AZ deployment. By default, we don't run multi-region. We can run multi-region if that's a requirement for your application. But by default, we just run multi-AZ. I think if an availability zone like US East 1 would suddenly entirely disappear, there's bigger problems than your database. So right now, multi-AZ is the default. Multi-region is possible. And for the durability guarantee, we run our MySQLs with semi-sync replication. And we require a cross-AZ acknowledgement. So every commit that goes to MySQL will be replicated. The binary log will be replicated to another availability zone. And at least one of those replicas in a different availability zone will have to acknowledge that it received a transaction before the client gets the acknowledgement like, this commit is good. So that's important. For Postgres, we do the same or the similar thing. We have, by default, 2 replicas, 2 standbys in another availability zone. And we require at least one of them to synchronously acknowledge that the commit is there. And this is the place where we had to patch Postgres, because in Postgres there's an option for the client to cancel a transaction, but cancel doesn't really roll back the transaction. The transaction is already committed, but cancel just cancels the replication to one of your replicas. And at that point in time, you would end up with a committed transaction on your primary that gets an acknowledgement back to the client, but it's never replicated to one of your replicas. So you don't have a guarantee that this is safe. So that's why we did a small patch to Postgres to make sure that if there's no acknowledgement from any of the replicas, that if you do a cancel, that we just refuse that. That was a requirement for our system to become available online, because otherwise we couldn't guarantee durability of your data. To make sure that we don't lose any data, we also do daily full backups of all our MySQL and Postgres instances. And we also do a full verification of those backups every day. So a default backup process at SCaLE looks like this. We spin up a new machine, a new pod in Kubernetes, and we restore the latest successful backup. We hook it up in replication. We let it replicate for a while, and then we say, okay, this is working well. We stop the instance and we copy the data directory to the cloud, to the object storage in the cloud, to Google cloud storage in GCP or to S3 in AWS. Another thing that we do for any upgrades that we do, like our system is a fully managed service in the cloud, so we also make sure that we keep up to date with any patches that need to happen. Like recently there was a CVE found in Postgres, which was quite bad. And we had to patch all of our things to make sure that we were not vulnerable. So what we do in the metal offering, what we do in the non-metal offering, like running on the EBS or persistent disk, is we take a replica out, we upgrade it, we put it back, let it replicate, go to the next one, repeat the process. At the end of when all our replicas have been upgraded or patched, we will promote a new primary, and then we do the same process to the old primary. We cannot do that in metal because we need our durability guarantee, so we want to make sure that we always have 3 copies of the data. So what we do is we search for upgrades. So we add new replicas, new instances to the cluster, and we run those in the new version. We replicate them, and then one by one we take the old replicas out of the equation, and then finally we promote a new replica, a new primary from one of the new installed replicas in the newer version to become the new primary, and then we finally decommission the old primary. Any questions?
Just what the splitting process looks like.
The what process?
The splitting process.
Splitting.
Like when a primary gets too large.
Okay, yes. So that is part of our Vitesse offering. Our Postgres offering currently doesn't do that yet. So Vitesse has a feature called v-replication. And v-replication is what we use to do multiple things. Like initially, it's a process that we use to do imports, like import data from an existing database, we replicate it in. But it also is the process that we use for shard splitting. So if you have a primary that grows too big for the server that you're on, we start a new key space, is what we call that in Vitesse terms, in the new sharded way, so 2 shards, 4 shards, 8 shards, however many shards you need. And then we do a v-replication process to copy the data to the new sharded environment. And then finally, we switch over the traffic to the new key space, and we decommission the old one. What v-replication looks like is it will first run a select star from table, start streaming all the rows to the new key space, and then it catches up on the binary logs of MySQL to bring the target table up to speed. View replication is really powerful. It can do filters on where you want to get the data to go sharding wise, but it also works for our online DDL solution that we use at PlanScale to do schema changes. So it can also convert the data on the source table to the new format of any altered table.
More questions? I have a couple.
Yeah,
One
sure.
is, so it sounds like the Postgres version is going to be a separate project.
It is.
From Vitess.
Yes,
Okay.
we're not trying to adapt Vitess to Postgres. We're basically rebuilding it from the ground up with all the learnings that we did from Vitess. And building it specifically for Postgres, so they are separate things, but we still use the expertise that we built up over the years.
You mentioned the data is all ephemeral. How do you hydrate it for the very first time when somebody's like booting up a new instance? How do you get it from the object store or the backup or the replica?
Yes, so if you start up a new instance, we restore a backup. We hook it up in replication. Like for every upgrade that we do the surging. So basically, we start up a new instance, we restore the latest backup, we hook it up in replication, which is the process that we do every day for our backup method. So we know that this will work because we did it at least 24 hours ago. It still works. So we are quite confident that our backups are always gonna restore. If you do an initial new database, you start with an empty database, and you do an import from wherever you're coming from. So that's how that gets done. Yeah?
A follow-on to that is, after a while, if you have a write-heavy database, the backup and restore and creating a new instance always gets, the provisioning time gets bigger and bigger.
Yes.
So how do you manage to load the minimum working set of the database based on the workloads?
So that depends on the customer. Like if you really start growing very, very quickly, we will shard your data into smaller segments. So that at that point in time, instead of one giant 100 terabyte database, you might have 100 shards of 1 terabyte, and we can all back up and restore them in parallel. So those backups are really, really fast. While in Postgres currently, there is no such solution yet. So there it really is, the time is growing as the data keeps on growing. So we tell potential customers that are coming in with hundreds of terabytes of data in Postgres, either to migrate to Vitess to get them sharded, or to wait for migration until the new Postgres product that we named Niki is coming out, and we hope to release that later this year, depending on how the development and testing is going.
Another one from me. I'm curious as to what would be different about the storage setup if somebody was running on their own metal.
If you're running on your own metal, like your own bare metal server in your data center, that would just work fine. The biggest issue is we run everything in Kubernetes. Like the biggest issue then is what's the lead time for you to provision a new server if you need to upgrade? Like all of our machines are upgraded every 30 days for security patches, so we don't have any databases that are hundreds of days running. We reboot everything and patch everything at least every 30 days. So we do this upgrade process like continuously to continuously test the process and to continuously also replace the machines for security updates and all of those things. So if you would, technically it would work running it in your own data center with your own Kubernetes. It's just much more difficult to provision new machines.
Okay. Well, thank you very much.
My pleasure.
We will have one more session today in the Cloud Native track just in Ballroom A. There will not be a session in this room. And then, of course, don't forget about game night, which is tonight. Thanks, everybody.